Hello there, and welcome to Physics with William, where complicated science is given a comfortable chair, a warm drink, and enough time to explain itself properly. Tonight we are going to meet a metal that does not look especially dramatic at first glance. It does not glow in the dark. It does not leap toward a magnet. It does not fizz when placed in water, and it has never enjoyed the household fame of iron, gold, silver, or copper. Yet place a small piece of it in your hand, and your first reaction would probably be surprise. It would feel far heavier than its size suggests, as though someone had managed to squeeze a much larger object into a very small space. That metal is osmium, commonly described as the densest naturally occurring element on Earth. Before we settle into its story, where are you listening from tonight? Are you somewhere quiet, perhaps already in bed, or are you still moving through the last few tasks of the day? And what is the heaviest small object you have ever held? Perhaps it was a paperweight, an old brass ornament, a compact tool, or one of those surprisingly serious hotel key rings designed to make sure nobody accidentally takes the room home with them. If you enjoy calm journeys through the stranger parts of science, you can leave a like and subscribe to the channel. It helps this small corner of thoughtful physics reach more people who might enjoy learning without being shouted at by flashing graphics. For now, let your shoulders relax, make yourself comfortable, and imagine that someone places a neat metal cube on the table beside you. It is small enough to hide beneath an ordinary teacup. It is smooth, silvery, and slightly blue in colour. Nothing about it appears unreasonable. Then you try to lift it. The word heavy can mean several different things, so it's worth being careful before osmium begins collecting titles it has not technically earned. Osmium is not the element with the heaviest individual atoms. Several elements have atoms with greater mass. Some are naturally occurring, while others are created in laboratories and survive only briefly. Osmium is called the heaviest material in everyday conversation because of its density. Density tells us how much matter is packed into a particular amount of space. A large object can be heavy simply because there is a great deal of it. A small object made from a very dense material can also be heavy because its atoms are packed into that space with remarkable efficiency. A litre of water has a mass of about 1 kilogram. The same volume of lead would have a mass of a little more than 11 kilograms. A litre of osmium would have a mass of roughly 22.5 kilograms. That is about the mass of a packed airline suitcase, compressed into the volume of a large bottle. You could place it on a kitchen counter, although the counter might wish you had chosen a less educational activity. The accepted density of osmium is close to 22.6 grams per cubic centimetre. The Royal Society of Chemistry lists it as the densest element and notes that it is about twice as dense as lead. Iridium is extremely close, and scientific references have sometimes treated the contest between the two as less settled than popular lists suggest. Measurements and calculations can produce slightly different rankings because density depends on precise crystal structure, temperature, pressure, and the quality of the sample. In ordinary scientific descriptions, however, osmium is usually given first place, with iridium standing so close behind that the difference would be hopelessly unimpressive in a sporting commentary. This closeness is useful because it reminds us that scientific records are not always carved into stone. Sometimes they are written in careful pencil with a note in the margin. Osmium does not need to defeat iridium by a dramatic distance to be interesting. Even if the two metals exchange places in a future measurement, osmium would remain one of the densest substances found in nature, and its unusual character would not become any less remarkable. To picture its density more clearly, imagine a cube with sides a little longer than 2.5 centimetres. That is roughly the width of a large grape or the thickness of a modest stack of coins. If the cube were made from aluminium, it would weigh about 44 grams. If it were made from iron, it would weigh around 129 grams. Made from osmium, it would weigh close to 370 grams. Your eyes would prepare your hand for something light, while the object would respond with the quiet confidence of a brick. That mismatch between appearance and weight is one reason dense materials feel so strange. Human beings become skilled at predicting weight from size. We learn through thousands of ordinary encounters with wood, glass, stone, plastic, food, tools, books, mugs, and the occasional parcel ordered online at an hour when our judgment was not at its best. When a small object is much heavier than expected, the brain briefly suspects a trick. Osmium would produce that reaction very effectively. Its density begins at the atomic level, but the explanation is not simply that osmium atoms are heavy. Gold atoms are slightly heavier on average, yet gold is less dense. Density depends both on the mass of the atoms and on how closely they are arranged in the solid. Osmium combines relatively massive atoms with a compact crystal structure. Its atoms settle into an arrangement that leaves little unused room, rather like careful travellers packing a car boot, while one determined person insists that the folding chair can still fit. The result is a metal in which a great deal of mass occupies very little volume. This does not mean the atoms are touching like marbles in a jar. Atoms are not tiny solid balls with clean outer surfaces. Their structure is governed by nuclei, electrons, and the rules of quantum physics. Most of what we casually call the size of an atom involves the region where its electrons are likely to be found. Still, when atoms form a solid, the distances between their nuclei and the pattern in which they arrange themselves determine how compact the material becomes. Osmium happens to combine the right atomic mass and the right arrangement to create an extraordinary overall density. On the periodic table, osmium belongs to a family known as the platinum group metals. The family includes platinum, palladium, rhodium, ruthenium, iridium, and osmium. These metals share several chemical qualities and are often found together in nature. They are known for resisting corrosion, tolerating high temperatures, and helping chemical reactions proceed without being consumed in the process. They are also rare, difficult to separate, and generally unwilling to make life easy for the people trying to obtain them. The United States Geological Survey describes the platinum group elements as metals with similar physical and chemical properties that tend to occur together and are mined in only a limited number of places. Osmium sits at atomic number 76. That number tells us that every osmium atom has 76 protons in its nucleus. Change the number of protons and the atom is no longer osmium. Add 1 and it becomes iridium. Remove 1 and it becomes rhenium. The identity of an element is therefore fixed by a count taking place in a region far smaller than anything the eye could see. At room temperature, pure osmium is a solid metal with a lustrous appearance that is often described as bluish white or silver blue. It can reflect light attractively, but it is not a soft decorative metal like gold. Osmium is extremely hard and brittle. Try to bend a piece and it is more likely to crack than politely change shape. This makes it difficult to form into useful objects. A blacksmith would not choose it for a relaxing afternoon. Its melting point is also exceptionally high, a little above 3000 degrees Celsius. That quality once made osmium attractive for specialised applications where ordinary metals could not tolerate the heat. Yet a high melting point creates an obvious manufacturing problem. Before you can cast a metal into a shape, you usually need to melt it. Osmium responds to that plan by demanding temperatures found in equipment rather more serious than a kitchen oven. The Royal Society of Chemistry lists its melting point at just over 3000 degrees Celsius and describes it as hard, corrosion-resistant, and useful mainly in specialised alloys, catalysts, electrical contacts, instrument pivots, needles, and durable pen tips. This is where osmium begins to seem slightly contrary. It is dense enough to attract attention, rare enough to sound valuable, hard enough to resist wear, and stable enough to survive difficult conditions. At the same time, it is brittle, challenging to shape, scarce, and associated with a chemical compound that requires great care. It possesses several impressive qualities. but it refuses to arrange them into the convenient combination that would make it an everyday construction material. You will not see buildings supported by osmium beams. Cars are not fitted with osmium doors. Nobody sensible is proposing an osmium frying pan, although it would remain firmly on the hob during even the most energetic cooking. Its density would make many ordinary products absurdly heavy, while its rarity and difficulty of manufacture would make them absurdly expensive. Engineering is not a competition to select the material with the most dramatic property. A useful material must balance strength, weight, cost, durability, safety, availability, and ease of production. Osmium arrives with one record-breaking feature and several pages of conditions. There is also an important distinction between solid osmium metal and one of its best-known compounds, osmium tetroxide. Bulk osmium is not something a person should handle casually, but the greater concern appears when osmium is finely divided or reacts with oxygen to form osmium tetroxide. This compound is volatile, highly toxic, and dangerous to the eyes and lungs. It is used under controlled conditions in laboratories, particularly when scientists need to prepare biological material for detailed imaging. Its ability to react strongly with certain parts of cells makes it useful, but usefulness does not make it friendly. This may sound alarming, especially in a program intended to help you relax, but there is no hidden cube of osmium quietly evaporating in the average bedroom. The point is simply that elements can behave very differently depending on the form they take. Carbon can appear as soft graphite or hard diamond. Oxygen is essential in the air, yet becomes hazardous under the wrong conditions. Sodium is a reactive metal, while sodium joined with chlorine helps season chips. Chemistry is full of substances whose behavior depends on structure, bonding, concentration, and environment. Osmium follows the same rule, with a little more paperwork. Its rarity adds another layer to its reputation. Osmium is present in Earth's crust only in tiny amounts, and is usually obtained as a byproduct when ores containing nickel, copper, and other platinum group metals are processed. It does not often gather into convenient lumps waiting beneath a sign marked rare metal here. The platinum group metals tend to occur together, and separating them requires a long sequence of chemical treatments. By the time pure osmium appears, a considerable amount of ore, energy, equipment, and patience has already been involved. This helps explain why people sometimes describe osmium as one of the rarest elements in the crust. It also explains why simple statements about its yearly production can be difficult to verify. Osmium is not usually mined in the way iron or aluminium are mined. It emerges from the processing of other materials, and figures may be combined with those of related platinum group metals. Supply is connected to a small number of mining regions and to industries that are mainly searching for platinum, palladium, nickel, or copper. Osmium is often the quiet passenger in a much larger operation. Rarity, however, does not automatically produce usefulness. A substance can be rare because nature makes little of it, because it's spread too thinly to collect, or because it is difficult to isolate. Markets also depend on demand. Gold is rare, but people have wanted it for decoration, money, electronics, and investment for a very long time. Osmium has important specialized roles, yet there is no vast global need to turn it into teaspoons. Its value therefore comes from an unusual mixture of scarcity, processing difficulty, limited supply, and niche demand. There is a temptation to hear the phrase densest element, and imagine that osmium must be the strongest metal as well. Density and strength are not the same property. A dense material contains a great deal of mass in a given volume. Strength describes how it responds to forces such as pulling, squeezing, bending, or impact. Lead is dense but soft. Tungsten is dense and very hard. Titanium is much less dense than osmium but has an excellent strength compared with its mass, which is one reason it is useful in aircraft and medical implants. Osmium is hard, but its brittleness limits what can be done with it. Nor does density mean that osmium has unusually strong gravity in any practical sense. Every object with mass produces gravity, but a small piece of osmium would not pull teaspoons across a table, or alter the path of a nearby biscuit. Its gravitational effect would be no greater than that of any other object with the same total mass. A 1 kilogram block of osmium and a 1 kilogram bag of flour produce essentially the same gravitational pull at the same distance. Osmium simply fits that kilogram into a smaller space and makes fewer clouds when dropped. It is also useful to separate mass from weight. Mass describes the amount of matter in an object. Weight describes the force of gravity acting on that mass. Take a piece of osmium to the moon, and its mass remains the same, but its weight becomes much lower because lunar gravity is weaker. It would still be an exceptionally dense metal. It would simply be easier to lift, which might be the most expensive way ever devised to improve a gym session. On Earth, the appeal of osmium comes partly from how directly we can feel density. Many scientific properties are hidden. You cannot look at an object and see its atomic number. You cannot easily sense its melting point without creating a situation that would concern the neighbours. Density can be experienced at once. Hold a dense object and your muscles receive the information before your conscious mind has finished making its prediction. Osmium turns an atomic arrangement into a physical surprise. That surprise can help us think more carefully about matter in general. The objects around us appear solid and continuous, but they are built from atoms arranged in different ways. Change the atoms, change the arrangement, or change the bonds between them, and the material can behave completely differently. Carbon can mark paper as graphite or scratch glass as diamond. Iron can form a soft, pure metal or become part of a strong steel alloy. Silicon can sit in rock or carry information through a computer. Osmium demonstrates another possibility. Matter can become so tightly packed that a small object feels almost incorrectly heavy. Yet the densest element on the table is not the densest material that can exist under all conditions. Deep inside planets and stars, pressure forces matter into states far denser than osmium. In a white dwarf star, matter is compressed to an extent that makes any terrestrial metal seem spacious. In a neutron star, the compression becomes more extreme still. A small amount of neutron star material, if it could somehow be removed and remain stable, would have a mass beyond ordinary experience. Osmium holds its title only within the familiar conditions of solid elements at or near the surface of Earth. That qualification does not diminish it. Records in science are always attached to conditions. Water boils at a certain temperature only at a specified pressure. Sound travels at a particular speed only in a particular medium and at a particular temperature. A material can be the hardest under one method of testing and behave differently under another. Osmium is the densest naturally occurring element under ordinary conditions, not the final answer to every possible question about compressed matter. The phrase on Earth also invites another thought. Osmium did not begin on Earth. The atoms in the metal were formed through nuclear processes associated with stars and violent cosmic events, long before our planet existed. Earth inherited them from older material that gathered into the young solar system. Every sample of osmium is therefore ancient, but so is the iron in a nail and the calcium in your bones. What makes osmium unusual is not simply its age. It is the rare chain of events that created it, scattered it, included it in our planet, hid it among other metals, and eventually allowed human beings to separate and identify it. For most of history, nobody knew osmium existed as a distinct element. People encountered ores containing it without having a name for it. Even skilled metalworkers could not simply look at a dark residue and announce that atomic number 76 had arrived. The element was concealed among platinum group metals, whose chemistry is similar enough to make separation difficult. Finding it required better laboratory methods and a growing understanding that familiar materials might contain several previously unknown elements. That discovery also gave osmium one of the more memorable names on the periodic table. It was not named after a country, a planet, a famous scientist, or a heroic figure from mythology. Its name came from an odour noticed during the chemical work that revealed it. This is a slightly awkward introduction for a metal now promoted for rarity and prestige. Imagine attending a formal dinner and learning that the distinguished guest at the far end of the table was named after the smell produced during an experiment. Chemistry has never been overly concerned with social comfort. The smell did not come from a polished block of metallic osmium. It came from a volatile compound formed during processing. That detail matters because it connects the discovery, the name, and the modern safety concerns surrounding osmium chemistry. It also takes us from the quiet weight of the finished metal into the much messier world of the early 19th century laboratories, where platinum ores, strong acids, stubborn residues, and careful observation led two chemists toward an element that had been present all along. To understand why osmium carries a name linked to smell and why its discovery was tied so closely to another rare metal, we need to return to London in the early 1800s, when a dark, insoluble residue refused to behave like waste. London at the beginning of the 19th century was not an especially gentle place for the nose. Coal smoke hung over the streets. Horses provided transport and a considerable amount of unwanted decoration. Open drains were still part of daily life, and the River Thames received substances that a modern environmental officer would prefer not to discuss before breakfast. In such a city, a bad smell had to work rather hard to distinguish itself. Osmium managed it. The trail begins with platinum, a metal that European chemists had known about for several decades, but still found difficult to understand and even harder to process. Much of the crude platinum reaching Europe came from South America, where miners had encountered heavy grey grains mixed with gold deposits. The material was sometimes called platina, meaning little silver, which sounds almost affectionate until one remembers that gold workers often considered it a nuisance. It resisted ordinary furnaces, refused to melt easily, and could contaminate gold. A metal that would later become a symbol of luxury first entered European workshops as an inconvenient grey interruption. Chemists were interested precisely because platinum behaved so stubbornly. Gold could be melted and shaped with established methods. Platinum demanded more imagination. It resisted corrosion, tolerated heat, and survived treatments that destroyed many familiar metals. Those qualities suggested that it might be useful for laboratory vessels and industrial equipment, provided anyone could persuade it to become a workable sheet, rather than a collection of difficult grains. Smithson Tennant and William Hyde Wollaston were among the people trying to solve that problem. Both men had trained in medicine, and both found chemistry more attractive than spending their days listening to patients describe mysterious aches. Around the start of the 19th century, they worked together on methods for purifying and shaping platinum. This was not simply academic curiosity. Reliable platinum vessels had commercial value because they could withstand strong chemicals and high temperatures. A successful process promised both scientific satisfaction and a respectable income, which is a pleasant combination when available. Tennant was already an accomplished experimental chemist. He had shown that diamond was made of carbon, a conclusion that would have been enough to secure a comfortable place in scientific history. Proving that a clear, glittering diamond and a piece of black carbon were made from the same element required the sort of mind that did not trust appearances. That habit would serve him well again. Where other people saw waste at the bottom of a vessel, Tennant saw an unanswered question. The platinum was treated with aqua regia, a powerful mixture of acids famous for its ability to dissolve noble metals. Its traditional name means royal water because it can attack gold, the metal once treated as royalty among materials. Platinum can also be brought into solution by this mixture, although the process requires care and patience. After the main portion had dissolved, a black powder remained at the bottom. Most people working with crude platinum knew about this residue. It was dark, stubborn, and apparently useless. Some assumed it was graphite or some other familiar impurity. That was a reasonable guess. Ores are rarely neat. They arrive with sand, rock, and traces of other substances, rather like a suitcase packed by geology, with without any concern for organisation. Once the valuable material has been removed, the dark leftovers are easy to dismiss. Tennant did not dismiss them. He noticed that the residue behaved as though it contained metallic matter that had not yet been identified. He also found it surprisingly dense. The powder had survived a chemical treatment strong enough to dissolve platinum, so whatever it contained was not going to introduce itself politely. It would need to be separated through a sequence of reactions, each designed to reveal a different property. This is one of the quieter skills in chemistry. Discovery is often described as a sudden moment, with a flash of insight followed by someone shouting that a new element has appeared. The laboratory version is usually slower. A substance is heated, washed, filtered, dried, weighed, treated again, and watched carefully. Results are compared, assumptions are questioned. Glassware accumulates in places where clean glassware used to be. Eventually, a pattern becomes difficult to explain using anything already known. Tennant heated the black residue with an alkali. After the heated material had cooled, he added water. At that point, one of the products entered the air and announced itself through a strong and peculiar odour. The smell came from a volatile oxide of the unknown metal, not from a solid piece of polished osmium. This distinction is important. The metal itself was not sitting in the crucible like an unusually offensive coin. A chemical reaction had produced a compound capable of escaping into the air. Tennant described the odour as pungent and peculiar. Later accounts often call it penetrating, acrid, or chlorine-like. None of these words suggest that anyone considered bottling it for the drawing room. The substance responsible was what we now call osmium tetroxide. It can form when osmium is exposed to oxidizing conditions, especially when the metal is powdered or finely divided. Unlike the dense metal, the tetroxide is volatile. It can pass into the air, reach the nose, and create an impression strong enough to name an element. That name came from the Greek word osm, meaning smell or odour. Tennant explained that the smell was one of the new metal's most distinguishing characteristics, so he proposed calling the metal osmium. This was practical scientific naming. He had found a property that separated the substance from others, and he used it as a label. There was no committee meeting about whether the name had sufficient dignity. The evidence arrived in the air, and the element has carried the result ever since. It is a curious fate. Gold was given a name with ancient roots and thousands of years of admiration behind it. Helium was named in connection with the sun. Uranium was linked to a planet. Promethium borrowed from mythology. Osmium was named because part of the experiment smelled terrible. The periodic table contains grand references to nations, scientists, gods, planets, colours and places. Then osmium enters and reminds everyone to open a window. The odour was useful because smell can be an extremely sensitive form of detection. The human nose can notice tiny amounts of some airborne chemicals. Long before electronic sensors became common, chemists paid close attention to odour, colour, texture, and even taste. Tasting laboratory substances is no longer regarded as a wise method, for reasons that become obvious after reading almost any old chemical manual. Smell also requires strict caution. Modern chemists do not place their noses over a vessel and breathe deeply. When odour must be checked in a safe teaching context, vapour may be gently wafted from a distance, and hazardous substances are handled in enclosed ventilation systems. Osmium tetroxide deserves much more than casual caution. It is highly toxic and can severely injure the eyes, skin and respiratory system. It is used only under controlled conditions by trained people with suitable protective equipment and ventilation. The fact that Tennant detected it by smell belongs to the history of chemistry, not to a list of experiments worth repeating at home. A person does not need to experience every scientific observation personally. We are all comfortable accepting the temperature of the sun without placing a hand nearby. The strange part is that osmium tetroxide is not merely a troublesome byproduct. Its reactivity later became valuable. It interacts strongly with certain biological materials, particularly lipids, and it has been used to preserve and stain tissue for microscopy. In electron microscopy, researchers need structures inside cells to produce enough contrast to be visible. Osmium compounds can help make membranes and other fatty structures stand out. The same chemical behavior that makes the substance hazardous also makes it useful when handled correctly. Chemistry frequently refuses to divide the world into substances that are simply good and substances that are simply bad. Context does most of the work. Back in Tennant's laboratory, the smell was only one clue. He still needed to show that the black residue contained a new metal and not merely an unusual compound of something familiar. This required transforming the material in different ways and observing whether the same distinctive behavior returned. He separated the volatile oxide by acidifying and distilling the solution. The oxide could condense as a pale material, then be converted through further reactions into a dark metallic powder. Step by step, the hidden substance became more definite. Another metal was concealed in the same residue. After removing the osmium-containing portion, Tennant worked with the remaining material and obtained solutions displaying a striking range of colours. These colours led him to call the second metal iridium, after Iris, the rainbow. The two elements therefore emerge from the same unpromising black powder with completely different introductions. Iridium arrived dressed in changing colours. Osmium arrived through the ventilation. The pairing makes the discovery easy to remember, but the work was not performed in complete isolation. French chemists had also examined the insoluble residue from platinum and recognised evidence of an unknown metal. Hippolyte Victor Collet Descotilles and the team of Antoine-François de Fourcroy and Nicolas-Louis Vauquelin reported observations related to what became iridium. Tennant acknowledged that other chemists had found the same new metallic ingredient, while noting that he had also identified a second unknown metal. Scientific discovery can involve several investigators, reaching parts of the answer at nearly the same time. Nature does not reserve an element for one appointment. Tennant presented his findings to the Royal Society in June of 1804. His paper carried a remarkably direct title, describing two metals found in the black powder left after platinum had been dissolved. There was no attempt to make the subject sound more dramatic than it was. The drama was already contained in the fact that a material treated as waste held two previously unknown elements. On that same day, Wollaston presented work on another new metal found in crude platinum. His investigations of the soluble portions and related materials had led to palladium and rhodium. Between the two business partners, platinum ore yielded 4 elements that now sit together in the platinum group. The ore had appeared to be one difficult metal with impurities. Careful analysis revealed a small gathering of chemical identities, each with its own behaviour. It is worth remembering that the periodic table did not yet exist. Tennant could not look at an empty position and say that an element ought to fit there. Atomic numbers had not been established, and the internal structure of atoms was unknown. Chemists identified elements through reactions, masses, colours, precipitates, resistance to heat, and the compounds they formed. They had to decide whether a substance was genuinely new, using tools far less direct than those available today. Modern laboratories can use instruments to analyse the light absorbed or emitted by atoms, measure masses with extraordinary precision, and determine crystal structures. Tennant had balances, furnaces, acids, alkalis, glass vessels, and observation. His equipment was simpler, but the reasoning was demanding. A new element could not be declared merely because a sample looked unfamiliar. It had to resist attempts to explain it as a mixture or a known substance in an unusual form. There was another complication. Producing a clean lump of osmium metal was extremely difficult. The metal has a very high melting point and is brittle. Early researchers often worked with powders, oxides, and salts, rather than a polished sample suitable for a museum display. The identity of the element was assembled from chemical evidence before anyone could casually pass around a neat blue-grey cube. This can feel surprising because modern pictures of the periodic table encourage us to imagine each element as a tidy sample in a labelled box. Real chemical history was rarely so organised. Some elements were known through gases, some appeared in mineral fragments. Others were inferred through lines of light or isolated in quantities barely visible. Osmium entered science through a resistant residue and a volatile compound. Its discovery looked less like unveiling a statue and more like sorting a cupboard whose contents objected to being sorted. The name also creates a common misunderstanding. A finished piece of solid osmium does not normally fill a room with an obvious smell. For something to be smelled, molecules or particles must reach receptors in the nose. A dense, stable block of metal releases very little material into the air. The danger rises with powdered or finely divided osmium and with conditions that allow osmium tetroxide to form. The compound is the source of the famous odour and the serious toxicity. Even the phrase "smell of osmium" is therefore a convenient shortcut. We often identify an element with the behaviour of one of its compounds. Chlorine is known for the smell associated with cleaning products, though household products contain chemical mixtures and should never be combined carelessly. Sulfur is blamed for the smell of rotten eggs, even though pure elemental sulfur is not the main culprit. Iron is associated with the metallic smell noticed on hands after touching coins or tools, but much of that odour comes from reactions involving skin oils. The nose reports chemistry, but it does not always provide a simple label. Osmium's name has nevertheless remained appropriate because the volatile oxide is unusually characteristic. The word survived changes in chemical language, improvements in atomic theory, and the creation of the periodic table. Its standard chemical abbreviation was later shortened to 2 letters, but in spoken narration the full name preserves the original observation. Every time someone says osmium, they repeat a small record of what happened when water met the heated alkaline residue in Tennant's experiment. Names matter because they carry history into ordinary use. A student can learn osmium as one more entry to memorize, but the name becomes easier to hold when it is connected to a real problem. Platinum had dissolved. Black powder remained. The powder was assumed to be unimportant. Tennant investigated it. A volatile compound produced a powerful odour. The odour suggested a name. This sequence is clear enough to remember without requiring a song about the periodic table, although such songs have rescued many exams. There is also a useful lesson in the residue itself. Scientific progress often depends on noticing what a successful process leaves behind. If the purpose of Tennant and Wollaston's work had only been to purify platinum, the black powder was a nuisance. If the purpose became understanding the material completely, the same powder was evidence. The difference lay not in the substance but in the question being asked. Waste products have led to important discoveries in many fields. Unexpected deposits, weak signals, failed reactions and contaminated samples can reveal something new when a researcher checks why the result did not match expectations. This does not mean every dirty flask contains an undiscovered element. Most dirty flasks contain exactly what a tired chemist suspects. Still, the habit of examining an anomaly rather than throwing it away is central to careful science. Tennant's work also shows why separating elements was so challenging. Osmium, iridium, platinum, palladium, rhodium, and ruthenium share several properties because they belong to the same region of the periodic table. In auras, they can occur together. Their similarities make them useful as a family but troublesome as individuals. Separating one from another can require repeated reactions that exploit relatively small differences. It is like trying to identify 6 nearly identical keys while wearing gloves, except some of the keys are expensive and one produces toxic vapour. The reward was not immediate public fame. Osmium did not transform daily life in the years after its discovery. It was too rare, too difficult to shape, and too awkward in some chemical forms. Small amounts eventually found specialised uses in hard-wearing alloys and components, but it never became a household metal. Most people could live an entire life without knowingly seeing a piece of it. The name remained better known to chemists, mineralogists, and the determined people who complete difficult crossword puzzles. Smithson Tennant did not have decades to develop the chemistry of the elements he found. He later became a professor of chemistry at Cambridge. In 1815, while travelling in France, he died after a bridge collapsed as he was crossing it on horseback. His life ended through an accident that had nothing to do with acids, furnaces, or volatile oxides. The elements, however, remained available for later scientists to investigate with better equipment and a growing understanding of atomic structure. As researchers learned more, osmium acquired an identity far broader than its smell. It was found to be extraordinarily resistant to heat, extremely hard, brittle, rare, and remarkably dense. The odour had supplied the name, but density supplied the reputation. Those two properties come from very different levels of chemistry. The smell belongs to a volatile compound able to move through air and interact with sensory receptors. The density belongs to the solid metal, where heavy atoms arrange themselves with exceptional compactness. That contrast is worth keeping in mind. Osmium can become noticeable by sending a tiny amount of compound into the air, yet the metal itself is defined by how much matter refuses to leave a tiny volume. One property spreads outward, the other packs inward. The first helped a chemist recognize the element. The second made the element famous. To understand why a piece of osmium feels so surprisingly heavy, the black powder and the laboratory smell are no longer enough. We have to look inside the solid, past its polished surface, toward the size of its atoms, the mass in their nuclei, and the unusually efficient way those atoms settle together. The answer begins inside the atom, in a region so small that ordinary ideas about size stop being helpful. Osmium has 76 protons in every nucleus, together with a larger collection of neutrons in its naturally occurring forms. Almost all of the atom's mass is concentrated in that nucleus. The electrons surrounding it contribute very little to the total weight, even though their behaviour determines how large the atom appears and how it bonds to its neighbours. Osmium therefore begins with a useful advantage in the density contest. Each atom carries a great deal of mass before the atoms have even started arranging themselves into a solid. A heavy atom alone, however, is not enough. Gold atoms are slightly heavier on average than osmium atoms, yet a block of gold is less dense than a block of osmium. Uranium atoms are much heavier, but uranium is also less dense under ordinary conditions. The important question is not merely how much mass one atom contains. We also have to ask how much room that atom and its neighbours require when they assemble into a metal. Density depends on both parts of the story. The guests must be heavy, but the seating plan must also be efficient. At room temperature, osmium has a density of about 22.5 grams in each cubic centimetre. The National Institute of Standards and Technology lists a value close to 22.6 grams per cubic centimetre, while Atomic Data place its atomic number at 76 and its standard atomic weight a little above 190. Under ordinary conditions, that combination makes osmium the densest elemental metal generally recognised at the surface of Earth. A cubic centimetre is not a large amount of space. It is roughly the volume of a small sugar cube, though sugar manufacturers are not required to maintain laboratory precision. Fill that space with water, and it has a mass of about 1 gram. Fill it with aluminium, and it has a mass of a little less than 3 grams. Fill it with iron, and it has a mass of nearly 8 grams. The same tiny space filled with osmium carries more than 22 grams. A handful of osmium would therefore feel less like a handful of metal, and more like a small objection from gravity. The atoms achieve this through a combination of high nuclear mass, relatively small atomic size, strong metallic bonding, and an orderly crystal arrangement. None of those features works alone. If the nuclei were heavy but the atoms remained far apart, the solid would occupy more space. If the atoms packed closely but each nucleus were light, the material would still not be especially dense. Osmium sits near a favourable meeting point. Its atoms are heavy enough to contribute substantial mass, compact enough to remain close, and organised in a structure that wastes little room. To understand the compact size, it helps to imagine the atom without picturing it as a hard ball. School diagrams often show electrons travelling around a nucleus like small planets around a star. That picture is useful for introducing the subject, but real electrons do not follow neat circular tracks. They occupy regions described by probabilities. These regions determine how the atom interacts with other atoms and how closely neighbouring nuclei can approach. Osmium belongs to a row of heavy elements in which the attraction from the nucleus is exceptionally strong. With 76 positively charged protons, the nucleus pulls firmly on the surrounding electrons. Inner electrons partly shield the outer electrons from that pull, but the shielding is not perfect. Some groups of inner electrons are less effective at blocking the nuclear attraction than we might expect. As a result, the outer parts of the atom are drawn inward more strongly, reducing the distances involved in bonding. This effect is connected to a broader pattern called the lanthanide contraction. Before reaching osmium in the periodic table, we pass through a sequence of elements in which a particular inner electron region is gradually filled. Those electrons do not shield the outer regions very efficiently. The increasing nuclear charge therefore pulls the outer electrons inward across the sequence. By the time we arrive at metals such as osmium, iridium and platinum, their atoms are more compact than a simple glance at their position in the table might suggest. There is another contribution that becomes important in very heavy atoms. The innermost electrons move in the intense electric field of a large nucleus, and their behaviour must be described using relativity as well as ordinary quantum mechanics. These relativistic effects alter the sizes and energies of electron regions. Some contract toward the nucleus, while others respond indirectly by expanding or shifting. In osmium, the overall electronic structure helps support short distances between neighbouring atoms and strong bonding. It is not a separate trick added after the rest of chemistry. It is part of the reason heavy elements do not behave like enlarged versions of lighter ones. Relativistic corrections to electron behaviour become increasingly significant as nuclear charge rises across the periodic table. The explanation can sound rather grand, but the practical result is simple. Osmium atoms can bring their nuclei unusually close together for atoms carrying so much mass. Picture a theatre in which every audience member arrives wearing a heavy winter coat, yet the seats have been arranged with remarkable economy. The building contains far more coat, person, and mild irritation per room than the theatre next door. Once the atoms come together, they adopt a structure known as hexagonal close packing. The name describes a repeating three-dimensional arrangement. If you placed equal spheres on a flat surface and pushed them together, each sphere would settle among 6 neighbours in a honeycomb pattern. A second layer could rest in the hollows of the first. A third layer could then repeat the position of the first layer. Continue the pattern, and you obtain the basic idea behind hexagonal close packing. Nature uses similar packing whenever round objects need to occupy space efficiently. Oranges in a market display settle into hollows between the oranges below them. Cannonballs in an old fortress could be stacked in the same general manner, preferably by someone with strong boots and a good understanding of consequences. The atomic version is not made from rigid spheres, but the model reveals how the arrangement minimizes empty space. In an ideal close-packed structure, nearly 3/4 of the available volume is occupied by the imagined atomic spheres. The remaining space lies in small gaps between them. Another common crystal arrangement, used by metals such as gold, can achieve the same ideal packing efficiency through a different stacking order. This tells us something important. Osmium is not dense simply because its crystal structure has discovered a method that every other metal somehow overlooked. Several metals pack efficiently. Osmium wins because its efficient packing is combined with very heavy atoms and short distances between their centres. Gold makes a useful comparison. Gold also forms a close-packed structure, and its atoms are slightly heavier on average. Yet the distances between gold atoms and the volume assigned to each atom in the crystal are larger. That extra space is enough to lower the overall density. Gold remains impressively dense, but osmium places a similar amount of atomic mass into a smaller average volume. It is the difference between two well-packed suitcases, one of which has been allowed a little more breathing room around every jumper. Iridium provides a much closer contest. Its atoms sit beside osmium in the periodic table, carry almost the same mass, and form a very compact metal. The measured densities are so close that older sources sometimes disagreed about which should take first place. Differences in temperature, sample purity, and the way crystal dimensions were measured could influence the result. Careful reviews of crystallographic data generally place osmium slightly ahead at room temperature and ordinary pressure, but the margin is tiny. Osmium is less a runaway champion than the winner of a race decided after everyone studies the photograph. Temperature matters because solids expand when heated. Their atoms vibrate more strongly and the average distances between them increase. The mass remains essentially the same, but the volume grows, so the density falls. Cooling usually has the opposite effect. This means that a statement about the densest element should include the conditions, even when those conditions are only quietly understood. At normal room temperature and pressure, osmium takes the familiar title. Change the temperature or pressure enough, and careful comparisons become more complicated. Purity matters as well. A real sample may contain traces of iridium, ruthenium, platinum, or other metals found in the same ores. It may also contain tiny pores, defects, or irregularities. A measured piece is not always a perfect crystal extending without interruption from one side to the other. Scientists can calculate density from atomic mass and precisely measured crystal dimensions, or they can measure the mass and volume of a physical specimen. Each approach has its own uncertainties. When two elements are separated by only a very small difference, those uncertainties deserve attention. Pressure introduces a different question. If you squeeze a material, its volume decreases and its density rises. Some materials surrender space easily. A foam cushion changes shape under the weight of a hand. A liquid compresses only slightly. A solid metal resists much more strongly because its atoms are already close, and its electrons resist being forced into the same regions. Osmium is exceptionally resistant to compression. Researchers have placed tiny samples between the tips of diamonds and applied pressures far beyond anything found in ordinary machinery. X-ray measurements show that its close-packed hexagonal structure survives under enormous compression, remaining recognizable even at pressures above 770 billion pascals. That is not merely a large number written to frighten a calculator. It is more than 7 million times ordinary atmospheric pressure. At first, osmium was even reported as less compressible than diamond. Later studies produced a more careful picture, and researchers have debated the exact comparison because results depend on pressure conditions, sample behavior, and how the data are interpreted. Density, hardness, and incompressibility are related only loosely. Diamond is much harder in the everyday sense of resisting scratches, while osmium is a dense metal that strongly resists a uniform reduction in volume. A material can excel at one test without winning every event in the materials Olympics. The resistance to compression comes from the energy required to push already close atoms even closer. Their electron regions begin to overlap more strongly, and quantum rules prevent electrons from simply piling into identical states. The material responds with increasing opposition. An ordinary sponge can reduce its volume by closing air-filled gaps. Osmium has no convenient network of large empty rooms to close. Its atomic hotel is already operating near an uncomfortable holiday weekend capacity. This does not mean osmium atoms are the smallest atoms in existence. Many lighter elements have smaller dimensions in certain definitions. Atomic size is not one universal measurement because an atom does not have a sharp outer wall. Scientists may discuss covalent radius, metallic radius, or other distances depending on the situation. What matters for density is the effective volume occupied by an osmium atom in its actual metallic crystal. In that environment, the heavy nuclei are separated by distances small enough to create an unusually large mass per volume. Nor does the crystal remain perfectly still. Even in a cold solid, atoms possess motion. At ordinary temperatures, they vibrate around average positions. The lattice is therefore more like a crowd standing in assigned places while shifting their feet than a frozen display of marbles. Heat increases the motion, the average spacing changes, and the density responds. At extremely low temperatures, the motion is reduced, though quantum physics prevents the atoms from becoming completely motionless. The presence of several natural isotopes adds another small detail. Every osmium atom has 76 protons, but different atoms can contain different numbers of neutrons. Those versions are called isotopes. Some are more common than others, and each has a slightly different mass. A natural sample contains a mixture, so the quoted atomic weight is an average shaped by their abundance. The most common naturally occurring isotope is among the heavier members of the mixture. This contributes to osmium's large average atomic mass, though the crystal arrangement and atomic volume are still essential to the final density. We can now see why simply moving farther down the periodic table does not guarantee a denser element. Atoms generally become heavier as their nuclei gain protons and neutrons, but their sizes, bonding, and crystal structures change as well. Some later elements occupy more volume, some adopt arrangements that are less compact, some exist only as radioactive laboratory products, making a normal block impossible to prepare. Density follows the balance between mass and volume, not a single march toward heavier nuclei. Lead illustrates the point nicely. Its atoms are heavy, and lead feels satisfyingly substantial in the hand, but it is only about half as dense as osmium. The lead atoms occupy more volume relative to their mass. Mercury is also heavy atomically, but its liquid structure at room temperature produces a density far below osmium. Tungsten approaches the density of gold and has an extremely high melting point, yet it does not pack as much mass into the same space as osmium. The periodic table is not a staircase with density rising neatly at every step. It is more like a street where each house has been designed by a different architect with strong opinions. A small cube makes the difference easier to imagine. Suppose we had equal cubes of wood, aluminium, iron, lead, gold, and osmium, each fitting comfortably in the palm. Their sizes would tell the eye that they should feel similar. The wooden cube would barely trouble the hand. Aluminium would feel light for a metal. Iron would feel reassuringly solid. Lead would arrive with a familiar heaviness. Gold would feel unexpectedly serious. Osmium would make the wrist question whether the demonstration had included concealed machinery. Increase the cube to 10 centimeters along each side, and the effect becomes less suitable for casual handling. That amount of osmium would occupy 1 liter and have a mass of more than 22 kilograms. It would be smaller than many household kettles, but heavier than most airline cabin luggage allowances. Dropping it would not create a new branch of physics, but it might create a new conversation with the owner of the floor. The gravitational pull of that cube would still be ordinary for its mass. Osmium does not intensify gravity merely because the mass is concentrated. At distances much larger than the cube, its attraction would be essentially the same as that of any other object with equal mass. Close to the surface, the compact shape can alter exactly how near you can bring another object to the mass, but the effect remains far too small to notice without sensitive equipment. The sensation of heaviness comes from Earth pulling on the cube and your hand providing the force needed to support it. Density also explains why osmium would sink in almost any familiar liquid. It would pass through water, oil, or mercury because each of those fluids is less dense. Even mercury, which can float pieces of iron, would not support osmium. The metal would descend with very little concern for the novelty of the situation. Buoyancy depends on the mass of fluid displaced. A small osmium object displaces too little ordinary fluid to balance its own mass. There are materials far denser than osmium elsewhere in the universe, but they do not exist as ordinary stable solids on a tabletop. In white dwarf stars, gravity compresses matter until electrons support the star against further collapse. Neutron stars go much farther, squeezing matter into conditions where the familiar structure of atoms no longer survives. Calling osmium the densest material on Earth is therefore a statement about accessible matter under ordinary conditions, not a claim that the universe has failed to imagine anything heavier. Even on Earth, enormous pressure deep underground changes density. Iron and other elements in the planet's interior are compressed beyond their surface values. Osmium remains useful to researchers partly because its resistance to compression and its electronic structure allow it to serve as an interesting comparison for materials under extreme conditions. The little metal that surprises a hand can also help scientists think about pressures found deep inside planets. The remarkable density, then, is not produced by one exotic feature. It is the combined result of a massive nucleus, imperfect electronic shielding, relativistic behavior in a heavy atom, short bonding distances in a close-packed crystal. Remove any major part of that combination, and osmium would lose its narrow advantage. Nature has not filled the metal with hidden weights. It has simply used atomic mass and space with unusual efficiency. That efficiency brings consequences beyond the number quoted in a reference table. Closely bound atoms help osmium resist compression. Strong bonding contributes to its high melting temperature. The compact structure helps produce a hard metal that does not yield easily to scratching or wear. Yet the same material can be brittle, difficult to shape, and troublesome to manufacture. Properties that sound similar in ordinary conversation begin to separate when the metal is tested. A dense metal is not automatically tough. A hard metal is not automatically flexible. A material that resists compression may still fracture when struck. Osmium carries all of these distinctions in a very small volume, which is why its physical behavior becomes even more surprising once someone tries to cut it, bend it, heat it, or turn it into something useful. A metal can be hard without being strong, strong without being tough, and heavy without being useful. Everyday language tends to place all these qualities in the same box, but material science separates them carefully. Osmium is an excellent reason to do that. It is exceptionally hard, highly resistant to wear, difficult to compress, and capable of surviving temperatures that would turn many familiar metals into liquid. Yet strike it in the wrong way and it can crack. Try to shape it like copper, and it may fracture rather than cooperate. Ask it to become an ordinary household material, and it responds with a long list of practical objections. A freshly prepared piece of osmium has a shiny silver appearance with a faint blue-grey tint. It can look smooth, calm, and almost decorative. Nothing on the surface announces that it is one of the most difficult metals to obtain and work with. It does not have the warm colour of gold or the immediate familiarity of silver. To an untrained eye, it might resemble a small piece of polished steel. The difference becomes clear when it is lifted, tested, heated, or taken into a laboratory where someone begins asking it increasingly personal chemical questions. The first surprise is its hardness. Hardness describes a material's resistance to scratching, indentation, or permanent damage at its surface. Osmium performs very well in this respect. Its atoms are held together strongly, and its closely packed structure does not allow them to slide past one another easily. This helped make osmium and its alloys useful in components that had to endure repeated contact, including old fountain pen tips, instrument pivots, needles, and electrical contacts. A soft material would wear away too quickly in those situations. Osmium could survive thousands of small movements with little complaint. Hardness is not the same as toughness. Toughness describes how much energy a material can absorb before it breaks. A rubber sole is not particularly hard, but it can bend, stretch, and survive impacts. Glass is harder, yet it can shatter when dropped. Osmium belongs closest to the glass side of that comparison. It strongly resists being scratched or deformed, but it is brittle. Under enough stress, it may crack rather than bend. This seems contradictory only because human beings often associate hardness with invincibility. A hard object feels dependable, We imagine that it should survive anything. Materials have not agreed to this arrangement. Diamond can scratch almost every natural substance, but sharp impact can break it. Steel can be softer than certain ceramics while being much better at absorbing shocks. Osmium is impressively hard, but it lacks the forgiving behaviour that engineers often need. The reason lies partly in the way its atoms respond when force is applied. In metals such as copper, aluminium and gold, layers of atoms can move past one another through the crystal without the entire structure falling apart. This allows the metal to bend, stretch or flatten. Copper can be pulled into wires. Gold can be beaten into extremely thin sheets. Aluminium can be rolled into foil and wrapped around a sandwich that will later be forgotten at the back of a refrigerator. Osmium does not permit this sort of movement easily. Its crystal structure and strong bonding resist the motion of defects through the metal. That resistance contributes to hardness, but it also means stress cannot be relieved through gentle deformation. Instead of bending and redistributing the force, the material may concentrate it around a flaw. A small crack begins, grows, and travels through the sample. The object has gone from apparently solid to several smaller objects with very little warning. This makes pure osmium difficult to machine. Cutting tools must be harder than the surface they are cutting, and strong enough to withstand the pressure. Even when a tool can remove material, the brittleness of osmium raises the risk of chipping and cracking. Drilling, rolling, stamping, and forging are not simple operations. A factory prefers materials that behave predictably. Osmium behaves predictably too, but its prediction is often that the factory would have an easier day using something else. Heating does not solve the problem easily. Many metals become softer and more workable as their temperature rises. A blacksmith heats iron so it can be hammered into shape. Glass workers heat glass until it flows. Osmium has a melting point above 3000 degrees Celsius, placing it among the most heat-resistant elements. Reaching that temperature requires specialized equipment, and the conditions must be controlled carefully because finely divided osmium can react with oxygen and form hazardous osmium tetroxide. Even before melting, high-temperature work with osmium is challenging. Ordinary furnaces may be unable to provide enough heat. Containers and tools must survive the same environment. The metal can contaminate equipment, and oxygen must be kept under control. Manufacturing a small component can therefore require far more effort than the component's size would suggest. A piece no larger than the end of a pen may carry the production history of a much more dramatic object. Corrosion resistance adds another interesting quality. Osmium belongs to the platinum group metals, which are known for resisting chemical attack. A solid piece of compact osmium is not eager to react with air at room temperature. It does not rust in the familiar way iron does. This stability helped make the metal attractive for situations where a surface had to remain reliable over time. The word resistant must be used carefully. Osmium is not completely unreactive. When the metal is finely powdered, the exposed surface area increases enormously. More atoms come into contact with oxygen, and oxidation can produce osmium tetroxide. A large compact piece and a fine powder contain the same element, but they do not present the same risk. The powder offers oxygen many more places to react, rather like turning one large log into a pile of dry shavings, and then discovering that fire has developed a renewed interest. Osmium tetroxide is volatile and highly poisonous. It can harm the eyes, skin, and respiratory system, even at very low exposure levels. Laboratories that use it rely on sealed containers, ventilation, protective equipment, and strict handling procedures. The substance is valuable for specialized scientific work, especially in preparing biological material for electron microscopy. But it is not a chemical to approach through curiosity alone. This gives osmium a peculiar reputation. A polished sample may appear stable and harmless, while one of its compounds is dangerous enough to demand exceptional care. The metal resists many ordinary chemical attacks, yet under suitable conditions it produces a substance capable of travelling through air. It can sit quietly in a display case and still carry a name inherited from a smell. Many elements change character when they form compounds. Chlorine is a poisonous gas, but chlorine atoms become part of ordinary table salt when joined with sodium. Carbon can form soft graphite, hard diamond, living tissue, fuel, and invisible gases. Iron can exist in strong steel or crumble slowly into rust. Osmium's transformation is particularly striking because the dense, hard metal becomes part of a volatile compound. The element known for packing an extraordinary amount of mass into a tiny space can enter a form that refuses to remain in that space at all. Its rarity makes every practical difficulty more significant. The platinum group metals are among the rarest mineral commodities in Earth's crust, and osmium is one of the least abundant members of that already exclusive family. It is usually found alongside platinum, iridium, ruthenium, palladium, and rhodium, often in ores associated with nickel and copper. Mines are rarely opened for osmium alone. The metal is generally recovered as a byproduct, while larger industries pursue other materials. This means there is no convenient osmium mountain waiting to be carved into small cubes. A mining operation may process a vast quantity of rock to obtain valuable nickel, copper, platinum, or palladium. Tiny amounts of osmium follow through the system. They must then be separated from metals with similar chemical behavior. The rare element begins as a trace within a mixture and ends as a product only after a long chain of concentration, refining, and purification. Finding members of the same chemical family together sounds helpful until someone tries to separate them. Platinum group metals share many properties. They resist corrosion, form related compounds, and often respond to chemical treatments in similar ways. Separating osmium from its neighbours requires taking advantage of small differences with carefully controlled reactions. The process can involve repeated dissolving, filtering, heating, precipitating, and distilling. Each stage produces material that must be tested before the next stage begins. The volatile oxide that makes osmium hazardous can also help chemists separate it. Under controlled conditions, osmium may be converted into osmium tetroxide, which can be distilled away from less volatile materials. The compound is then collected and reduced to recover osmium in another form. This is effective chemistry, but it turns purification into a task involving one of the least friendly compounds in the laboratory. The element seems to have arranged matters so that obtaining it requires temporarily making it more dangerous. Modern industrial methods are carefully contained, but they cannot remove the fundamental inconvenience. A rare metal already demands efficient recovery because very little is available. Osmium adds difficult separation and strict safety requirements. Losses must be kept low, waste streams must be treated, equipment must resist aggressive chemicals, workers must be protected. By the time a small quantity of refined osmium is ready, its physical mass may be modest, but the amount of planning surrounding it is not. Exact production figures for osmium are difficult to isolate because mineral reports often group it with the other platinum group metals. Palladium and platinum dominate the market and receive most of the attention. Osmium, iridium, and ruthenium are usually produced in far smaller amounts, with supply depending on the processing of ores mined for more commercially important metals. The world does not decide each year how much osmium it wants and then send miners to collect that amount. It accepts whatever quantity can be economically recovered from a much larger operation. This makes the supply unusual. If demand for osmium suddenly rose, producers could not simply increase output in the way a bakery increases the number of loaves. More osmium would generally require more mining and processing of ores, whose main value comes from other metals. Producing a large amount purely to obtain osmium could be enormously wasteful. Its availability is tied to decisions made elsewhere in the mining industry. Rarity also encourages exaggerated claims. Osmium is sometimes advertised as though scarcity alone makes every sample an obvious investment. Prices quoted online can vary dramatically depending on purity, form, certification, and whether the material is being sold as a laboratory product, a collector's sample, or a decorative object. A price attached to a tiny manufactured bead does not necessarily represent a broad liquid market. Rare does not mean easy to resell, and expensive does not mean financially sensible. A bar of gold can be tested, weighed, and traded through established systems. Osmium has a far smaller market. Buyers may require specialized analysis to confirm purity. A sample could contain other platinum group metals, and appearance alone provides little certainty. The difference between a valuable specimen and a shiny object accompanied by confident paperwork may require equipment rather than optimism. The metal's brittleness creates another problem for decorative use. Jewellery must survive knocks, scratches, temperature changes, skin contact, and years of movement. Pure osmium would be a difficult choice for a ring or bracelet. It is dense enough to feel unusually heavy, but it cannot be shaped and repaired as easily as gold or platinum. Some commercial materials use treated or crystallized osmium surfaces, often as small inserts rather than large structural pieces. These objects rely on controlled production and careful mounting because the element's record-breaking density does not remove its mechanical limitations. Crystalline osmium can have a striking surface. Tiny crystal faces reflect light from different directions, producing bright flashes that may appear blue-grey or silvery. The effect has attracted interest from collectors and luxury designers, yet the visual appeal comes from surface structure, not from osmium becoming a new kind of gemstone. It remains a metal, and the beauty of the surface does not alter the difficulties beneath it. A large polished piece would also be uncomfortable to wear. A ring containing a substantial volume of osmium could place surprising pressure on the finger. Earrings made from it would turn a pleasant evening into a test of determination. A watch case might feel reassuringly substantial for several minutes, after which the wrist would begin composing a formal complaint. The density that makes osmium fascinating therefore works against many potential products. Engineers often spend enormous effort reducing mass. Aircraft, vehicles, portable electronics, medical devices and tools benefit from materials that provide strength without unnecessary weight. Osmium offers the opposite arrangement. It places as much mass as possible into the available space. This is useful only when high density itself provides an advantage or when the required component is extremely small. Counterweights are one possible use for dense materials. A small heavy piece can balance a larger moving system without occupying much room. Tungsten is commonly used because it is dense, strong, available in greater quantities, and easier to obtain at industrial scale. Osmium is denser, but the improvement is too small to justify the additional cost and difficulty in most applications. Engineering rarely pays a fortune to win a comparison that nobody outside the design office will notice. Radiation shielding provides another example. Dense materials can help block certain forms of radiation, but density is not the only consideration. Lead is widely used because it is relatively cheap and easy to shape. Tungsten is useful where higher performance and less toxicity are needed. Osmium would be costly, brittle, and difficult to manufacture into large protective structures. A shielding wall made from osmium would be impressively compact and economically memorable. Its electrical behavior is useful but not extraordinary enough to replace common conductors. Copper carries electricity very well and can be drawn into flexible wires. Silver conducts even better, though at a higher cost. Osmium can serve in durable electrical contacts when wear resistance matters, but nobody is preparing to rewire a house with it. The wires would be expensive, heavy, difficult to form, and likely to convert a simple renovation into a research program. Osmium is also not the best choice simply because a component must withstand heat. Tungsten has a higher melting point. Certain ceramics tolerate extreme temperatures and resist chemical attack. Nickel-based alloys combine heat resistance with mechanical toughness. Engineers choose among these materials according to the full environment, including pressure, vibration, oxidation, manufacturing method, and cost. Osmium may perform brilliantly in one category, while losing practical ground in several others. This is why it has remained a specialist rather than becoming an industrial celebrity. Iron is used in enormous quantities because it can be turned into steels with a wide range of properties. Aluminium is light, corrosion-resistant and easy to shape. Copper conducts electricity and heat. Titanium combines low density with strength and biological compatibility. Osmium offers density, hardness and chemical interest, but it does not provide the broad combination needed for widespread use. Its greatest value often appears when it is combined with other metals. Alloys can preserve some of osmium's hardness and wear resistance while reducing the brittleness or improving workability. Natural alloys of osmium and iridium were historically known and used for small, durable points and bearings. The names osmiridium and iridosmium were applied to mixtures with different proportions, though modern mineral classification is more precise. These materials could endure friction where softer metals would slowly wear away. An old fountain pen offers a good example. The tip repeatedly touches paper, changing direction and experiencing small forces with every letter. A soft tip can wear down and alter the writing feel. A tiny hard alloy point lasts much longer. Only a very small amount of material is required, so rarity and density become less troublesome. Osmium works best when the job is small, specialized and willing to pay for endurance. The same principle applied to instrument pivots and needles. A precision mechanism may depend on a tiny point supporting repeated motion. Wear of only a small amount can reduce accuracy. Hard platinum group alloys provided durable surfaces before modern engineered materials offered more alternatives. Osmium did not need to form the whole instrument. It only had to protect the part receiving the greatest punishment. There is a quiet pattern here. The metal possesses several extreme properties, yet each one brings a restriction. Its density is extraordinary, but it makes objects heavy. Its hardness resists wear, but its brittleness encourages fracture. Its high melting point permits survival at great heat, but complicates manufacturing. Its corrosion resistance provides stability, while oxidation in certain forms creates a dangerous volatile compound. Its rarity gives it fascination but limits availability. Osmium is not a collection of simple advantages. It is a collection of trade-offs arranged in a very small volume. That makes it more useful as a lesson in material science than as a universal supermetal. Popular descriptions often ask which metal is strongest, hardest, rarest, or heaviest, as though nature awards one overall prize. Engineers ask a longer set of questions. Strong under what kind of force? Hard against what surface? Stable at what temperature? Safe in what form? Available in what quantity? Affordable for what purpose? Repairable using what tools? Osmium can produce impressive answers to several of those questions and disappointing answers to the rest. This does not make it a failed material. It means that properties only become meaningful when attached to a task. A material unsuitable for a bridge may be perfect for the point of an instrument. A hazardous compound can become invaluable inside a controlled laboratory. A metal too rare for mass production can help researchers understand chemistry, geology, and the conditions inside planets. Even its rarity contains a larger question. Osmium is a heavy element with a large nucleus. The early universe did not begin with ready-made osmium atoms waiting to become part of a mine. Simple matter had to pass through generations of stars and violent nuclear events before nuclei this heavy could form. The metal is scarce in Earth's crust, partly because of what happened while the planet was assembling, but its story began much earlier, in environments where temperature, pressure, and streams of neutrons could build atoms far beyond iron. The small blue-grey sample on a laboratory table is therefore not only difficult to scratch, melt, bend, refine, and purchase. It is the surviving result of events that occurred before Earth had oceans, rocks, or anything resembling a periodic table, and following that trail takes us away from mines and furnaces toward the places where heavy elements were first made. The metal did not begin in a mine. Long before there were rocks, oceans, planets, or laboratories, the matter that would eventually become osmium was being assembled in places where temperatures and pressures were far beyond anything found on the surface of Earth. A sample of osmium may sit quietly on a table, but its nuclei record a history that began before the solar system existed. The early universe did not start with a complete collection of chemical elements. In the first minutes after the beginning of cosmic expansion, conditions allowed mostly hydrogen and helium to form, along with very small amounts of lithium. There was no iron, no gold, no uranium, and no osmium. The periodic table was mostly empty, although nobody was present to complain about the lack of stationery. As the universe expanded and cooled, gravity drew clouds of hydrogen and helium together. The centers of those clouds became hotter and denser until the first stars began to shine. Inside a star, light nuclei can be joined into heavier ones. Hydrogen becomes helium. In sufficiently massive stars, later stages can produce carbon, oxygen, neon, silicon, and elements around iron. Each stage requires higher temperatures and usually lasts for a shorter time than the one before it. This ordinary stellar fusion process is extremely effective for building elements up to the iron region. It also supplies the energy that supports a star against gravity. The situation changes near iron. Joining lighter nuclei can release energy, but joining iron into substantially heavier nuclei generally requires energy instead. A star cannot continue obtaining useful support by simply fusing iron into larger and larger atoms. The production line reaches a point where every additional order comes with a bill. Osmium lies far beyond iron on the periodic table. Its nucleus contains 76 protons, while iron contains 26. Building that difference by repeatedly forcing positively charged nuclei together would be difficult because positive charges repel one another. At the temperatures found in stars, some such reactions can occur, but they do not provide the main explanation for the abundance of very heavy elements. Nature uses a more convenient particle. That particle is the neutron. A neutron has no electric charge, so it can approach a nucleus without being repelled by the positive protons inside it. When a nucleus captures a neutron, it becomes a heavier isotope of the same element. The number of protons has not changed, so the chemical identity remains the same. The nucleus is simply carrying one more neutron than before. Some neutron-rich nuclei are unstable. One of their neutrons can transform in a process that leaves the nucleus with an additional proton. When that happens, the atom moves one position higher in the periodic table. Repeated neutron captures and radioactive changes can therefore build a path from relatively modest seed nuclei toward elements much heavier than iron. It is less like stacking entire atoms and more like adding small pieces, checking whether the structure is stable and then adding more. There are two major versions of this neutron capture route. They are known as the slow neutron capture process and the rapid neutron capture process. Slow and rapid do not describe how exciting the events appear through a telescope. They compare the rate of neutron capture with the rate at which unstable nuclei undergo radioactive change. The slow process operates where neutrons are available steadily but not in overwhelming numbers. A nucleus usually captures one neutron, then has time to change if it is unstable before another neutron arrives. This keeps the route relatively close to stable nuclei. The process takes place especially in aging stars of low and intermediate mass during a late phase of their lives, and it also contributes inside massive stars. These stars can produce neutrons through reactions occurring in their hot interiors, allowing iron group seed nuclei to grow step by step into heavier elements. Picture a careful clerk adding one item to a form, waiting for approval, and only then adding the next. The method is not dramatic, but it can continue for thousands of years. Over time, it produces many heavy nuclei, including part of the natural osmium found in the solar system. One naturally occurring isotope, osmium 186, is commonly classified as an isotope produced by the slow process, because other stable nuclei block the rapid process from reaching it through its normal decay route. This does not mean a star contains a neat workshop labelled Osmium Department. The reactions form a network involving many isotopes of many elements. A nucleus captures a neutron, another decays. A branching point opens because two outcomes are possible. Temperature and neutron supply change the probability of each route. The final mixture depends on the type of star, its original composition, its mass, and the conditions during each stage of its life. When an aging star loses its outer layers, the elements made inside it can be released into space. Some stars shed material through slow winds over long periods. The gas joins the interstellar medium, mixing with material from other stars. A single cloud can contain atoms produced by many previous generations, so even before violent events enter the story, the galaxy has already become a large and poorly labelled recycling system. The rapid neutron capture process works under very different conditions. Here the neutron supply is so intense that nuclei capture more neutrons before they have time to undergo ordinary radioactive changes. They are pushed far into unstable neutron-rich forms. When the neutron flood ends, those nuclei decay through a series of steps toward more stable arrangements. The process can produce very heavy elements and isotopes that the slow route cannot make in significant amounts. For decades, scientists debated where the rapid process occurred. Exploding massive stars were obvious candidates because they provide extreme temperature, pressure, and energy. Some rare kinds of supernova may still contribute. Another major site is the collision of two neutron stars. A neutron star is the compressed remnant left after certain massive stars explode. It packs more mass than the Sun into an object roughly the size of a city, so describing it as dense is rather like describing the ocean as slightly damp. Two neutron stars can orbit one another for millions or billions of years. Their orbit gradually shrinks as the system loses energy through gravitational waves. Eventually they collide. The merger throws out matter that is extraordinarily rich in neutrons. In that expanding debris, rapid neutron capture can build nuclei across the heavy end of the periodic table, including nuclei in the mass range occupied by osmium. An important observation arrived in August of 2017. Gravitational wave detectors recorded a signal from two merging neutron stars. Telescopes then observed light from the same event across several parts of the spectrum. The fading glow matched the expected behaviour of a kilonova, an event powered in part by the radioactive decay of newly formed heavy nuclei. The observations provided strong evidence that neutron star mergers are major factories for rapid process elements. Scientists did not hold up a spectroscope and read the word osmium from the explosion. Identifying individual heavy elements in the tangled light of a kilonova is extremely difficult. The evidence showed that the event produced a broad population of heavy nuclei, and models indicate that the conditions can create material reaching the region of gold, platinum, osmium, and beyond. The exact amounts depend on how much matter is ejected, how neutron-rich it is, how neutrinos alter its composition, and what object remains after the collision. The relative importance of different rapid process sites is still being studied. Neutron star mergers clearly contribute, but rare supernovae and other extreme stellar explosions may also be necessary to explain how early in galactic history some heavy elements appeared. A merger requires two neutron stars to form and then meet, which may take time. Some ancient stars contain rapid process material from very early generations, suggesting that at least part of the production must sometimes occur quickly. The current picture contains more than one possible factory rather than a single cosmic address. Wherever a particular osmium nucleus formed, the event was not gentle. A seed nucleus had to be exposed to neutrons, pushed into an unstable form, and allowed to decay toward a lasting isotope. The resulting atom was then ejected into space at high speed. It travelled through gas containing the remains of other stars. Shockwaves stirred that gas. Dust grains formed and were broken apart. New clouds gathered, carrying a mixture of elements with origins separated by enormous distances and times. Osmium does not have only one isotope, so natural osmium does not have only one route of origin. A normal terrestrial sample is a mixture of 7 naturally occurring isotopes. They all contain 76 protons, which makes them osmium, but they contain different numbers of neutrons. Their cosmic histories are not identical. Some receive substantial contributions from the rapid process. One has a special connection to the slow process. Another can be produced over time by the radioactive decay of rhenium. That last route involves rhenium-187. It is unstable, but it decays extremely slowly, with a half-life of roughly 42 billion years. When it decays, it becomes osmium-187. This means that some osmium atoms inside rocks were not present as osmium when the solar system formed. Their rhenium parents were created in earlier cosmic events, entered the young Earth, and later changed into osmium. Geologists use this relationship as a clock. Different minerals contain different proportions of rhenium and osmium. By measuring the isotopes carefully, researchers can estimate when certain rocks or ore deposits formed and study the history of Earth's mantle. The method works because the decay is slow and predictable. Osmium therefore records two kinds of history at once. Its heavy nuclei point back to stellar nucleosynthesis, while the changing balance between rhenium and osmium helps measure events that occurred after planets appeared. About 4.5 billion years ago, part of a large cloud of gas and dust collapsed to form the Sun and a surrounding disk. The material in that disk had already been enriched by older stars. It included hydrogen and helium from the early universe, carbon and oxygen from stellar fusion, and small quantities of heavy elements from neutron capture events. Osmium atoms were scattered thinly through this mixture, often associated with metal-rich grains. The young solar system sorted that material through heating, cooling, collisions, and gravity. Dust grains stuck together. Small bodies formed, then larger ones. Some became asteroids. Others collided to build planets. Meteorites that survive today preserve samples of those early materials. Their proportions of osmium and related elements help researchers compare primitive solar system matter with the composition of Earth and the Moon. During Earth's formation, the planet became hot enough for large portions to melt. Heat came from impacts, compression, and the decay of radioactive elements. Dense liquid iron moved inward, carrying with it elements that prefer metallic iron over silicate rock. Osmium has a strong tendency to enter metal. Geochemists describe it as highly siderophile, meaning strongly iron-loving. If Earth had separated perfectly into a metal core and a rocky mantle under simple equilibrium conditions, most osmium should have followed the iron into the core. That is probably where the largest share of Earth's osmium remains today, far below any mine. The planet may contain far more osmium than the crust suggests, but it has stored much of it several thousand kilometers down, which is an inconvenient place to establish a refining business. The mantle still contains measurable osmium, and its abundance has helped geologists reconstruct what happened after the main stage of core formation. One widely supported explanation is late accretion. After the core had largely separated, additional primitive bodies struck Earth and added small amounts of material rich in highly siderophile elements. Because the main pathway into the core was no longer operating in the same way, some of the osmium remained in the mantle. The exact details are still discussed. Researchers examine isotope ratios, meteorites, mantle rocks, experiments at high pressure, and comparisons with the Moon. Some models focus on a late veneer of chondritic material. Others investigate whether changing pressure, temperature, sulfur content, and incomplete equilibration during core formation could leave more osmium behind than simple models predict. Evidence from osmium and iridium strongly supports a substantial late contribution, but the early Earth was complicated enough that one tidy explanation rarely survives without footnotes. This history explains why osmium is so scarce near the surface. It was rare in the material that formed the solar system to begin with. Much of what entered the growing Earth preferred metal and moved toward the core. The small amount remaining in the mantle became spread through an enormous volume of rock. Only later, geological processes concentrated traces into places where they could eventually be found. Osmium is often associated with sulfide minerals and with other platinum group metals. Mantle-derived magma can collect these elements under suitable conditions, dense mineral grains can survive erosion and become concentrated in river deposits. Meteorites can also contain measurable osmium, carrying material that avoided the full process of planetary melting and differentiation. Each setting preserves a different part of the journey from stellar debris to a sample that fits inside a laboratory container. The idea that osmium was forged in stars is therefore correct but incomplete. Some of its isotopes were built slowly in aging stars. Much of the heavy material was assembled rapidly in neutron-rich catastrophes, such as neutron star mergers and perhaps rare stellar explosions. Some osmium appeared later through the decay of rhenium. The atoms were mixed into the cloud that formed the solar system, incorporated into the young Earth, drawn toward the core, and partly returned to the mantle by late-arriving material. By the time a miner encounters an osmium-bearing ore, nearly all of that history has become invisible. The rock does not glow with evidence of a neutron star collision. It does not carry a label showing which atoms came from an aging giant and which came from a violent merger. The clues survive in isotopic proportions and chemical associations, available only to instruments sensitive enough to separate almost identical atoms. What remains for industry is a very small amount of metal dispersed among other materials. Reaching it requires moving from astrophysics back to geology, then from geology into mines, crushing plants, chemical refineries, and sealed equipment designed to recover a substance that nature has made rare at every stage of its existence. The journey from a star to a laboratory sample is long, but the final part begins in a place that looks much more ordinary. There is rock, dust, heavy machinery, water, pipes, and people wearing protective equipment. Somewhere inside the rock are traces of platinum group metals, including an amount of osmium so small that nobody could identify it by sight. The ore does not contain bright blue-grey nuggets arranged conveniently near the entrance. Osmium is usually scattered through minerals alongside platinum, palladium, ruthenium, rhodium, iridium, nickel, copper, iron, sulfur, and a great deal of material that the refinery does not want. This is why osmium is almost never mined on its own. A company does not normally locate a rich seam of pure osmium, open a mine, and begin filling small, valuable buckets. It mines a much larger deposit for platinum group metals, nickel, copper, or some combination of them. Osmium follows as a minor companion. In many operations, it is a byproduct of a byproduct, which is a rather modest position for the densest element. Most known platinum group resources are concentrated in a small number of geological regions. The Bushveld complex in South Africa contains the largest known concentration. The Great Dyke in Zimbabwe is another major source, while important deposits also occur around Norilsk in Russia, Sudbury in Canada, and the Stillwater complex in the United States. These places were formed through different geological histories, but they share an association with large bodies of magnesium and iron-rich igneous rock, sulfide minerals, or layers rich in chromite. The 6 platinum group elements tend to occur together, which is useful for finding them and inconvenient for separating them. Before mining begins, geologists must determine whether the concentration is high enough to justify moving an enormous amount of rock. They map the surface, study magnetic and gravitational patterns, drill narrow holes, and remove cylinders of rock called cores. These cores are logged, photographed, cut, and sampled. Laboratories then measure concentrations that may amount to only a few grams of combined precious metals in a ton of ore, with osmium representing only a small fraction of that total. A ton is the mass of a small car. Imagine grinding an entire car into powder, searching through it for a few paper clips, then discovering that the paper clips are chemically similar to several other tiny objects mixed through the same powder. That gives a rough sense of the challenge, although actual ore has fewer seats and usually better mineral records. The first task is not to isolate osmium, it is to identify and follow the mineralized zone. In the Bushveld complex, valuable material can occur in relatively thin layers that extend across great distances. Some mines reach these layers through open pits, where the deposit is close to the surface. Others use underground shafts, tunnels, and sloping passages because the ore lies far below. The choice depends on depth, rock stability, cost, safety, and the geometry of the deposit. Underground mining requires ventilation, drainage, ground support, transport systems, and constant monitoring. Workers drill holes into the rock and use controlled blasting or mechanical equipment to break sections free. The broken ore is collected and carried to the surface. Waste rock must also be removed, because a tunnel does not politely pass only through the valuable material. At the surface, large pieces of ore enter crushers. The first machines reduce boulders to smaller fragments. Later crushers and grinding mills continue until much of the material has become a fine powder. This is necessary because the valuable minerals are locked inside the rock. A platinum group mineral may be far smaller than a grain of sand and may sit against or within a sulfide mineral. Until the surrounding rock is broken apart, the refinery cannot separate it effectively. Grinding must be controlled. If the particles remain too large, valuable minerals stay trapped and are lost with the waste. If the material is ground far more finely than necessary, the operation wastes energy and can make separation more difficult. Mining companies therefore study the ore under microscopes to learn how the valuable grains are distributed. The ideal particle size is a compromise between freeing the minerals and avoiding the production of an expensive grey soup. The powder is mixed with water to create a slurry. It then passes into flotation tanks, where selected chemicals are added and air is blown through the mixture. Certain mineral surfaces are encouraged to attach to bubbles. The bubbles rise and form a froth that can be collected, carrying a higher proportion of sulfides and platinum group minerals. Much of the unwanted rock remains in the water and settles elsewhere. Flotation does not pluck osmium atoms individually from the slurry. It concentrates mineral particles likely to contain the whole family of valuable metals. The process works because different mineral surfaces respond differently to water, air, and carefully chosen reagents. Real ores are complicated, and platinum group minerals do not all behave in the same way. Some are already free, some are attached to sulfides, some are enclosed in silicate or chromite. Researchers adjust grinding reagent mixtures, airflow, and the time spent in each tank to improve recovery. The froth concentrate contains much less waste rock than the original ore, but it is still far from pure. It may contain copper, nickel, iron, sulfur, and traces of all 6 platinum group metals, along with gold and other elements. The concentration step has made the valuable portion manageable. Instead of sending every ton of mined rock into the most expensive part of the refinery, the operation sends a much smaller mass of enriched material. The remaining slurry becomes tailings. These are stored, treated, or managed according to the design of the site. Tailings contain finely ground rock, water, and traces of processing chemicals. They require careful engineering because the volume is large and the particles can remain mobile when wet. Water may be recovered and reused, while dams and storage facilities must be monitored over long periods. This environmental part of mining is easy to overlook when admiring a polished metal sample. Osmium may occupy only a tiny glass container, but obtaining it can involve moving large amounts of earth and managing large amounts of waste. The value of the final material does not make the discarded rock disappear. Modern operations must consider water use, energy, air emissions, worker exposure, land disturbance, and what remains after the mine closes. Once dried, the concentrate is sent to a smelter. Here the material is heated in a furnace so that it separates into different molten portions. Much of the unwanted rocky material combines into a layer called slag. The valuable sulfide material forms a heavier molten product called matte, containing nickel, copper, iron, sulfur, and the precious metals. The furnace does not melt pure osmium into a tidy pool at the bottom. Its concentration is far too low, and it remains distributed among intermediate products. The goal is to remove bulk waste and gather the metals into a smaller mass. Refining rare elements is usually a sequence of concentration steps rather than one clever machine with a button marked osmium. The matte passes through further high-temperature treatment. Air or oxygen-enriched gas may be introduced to remove much of the iron and sulfur. Sulfur leaves mainly in gas that must be captured and treated, while iron joins as slag. The resulting material is richer in nickel, copper and platinum group metals. Every stage reduces the quantity that must be handled later, but each also creates streams that must be checked, because a tiny amount of osmium lost at several stages can become a meaningful part of the total supply. Base metal refining comes next. Nickel and copper are valuable products, not merely obstacles. Depending on the operation, they may be separated through chemical leaching, electrical refining, or a combination of methods. During electrical refining, an impure metal is placed in a solution and encouraged to dissolve and redeposit in purer form. Some substances do not follow. They collect as dark residues, often called anode slimes. The word slime does not suggest treasure. It sounds like something found beneath a neglected refrigerator. In a metal refinery, however, node slime can contain gold, silver, selenium, tellurium, and platinum group metals. As the bulk nickel or copper is removed, the rare materials become concentrated in the residue. One published recovery process from the Sudbury nickel and copper ores traced minute amounts of osmium through plant intermediates, collected material that had previously been lost, and refined it into metal powder of very high purity. By this point, the original ore has passed through blasting, crushing, grinding, flotation, smelting, converting, and base metal separation. The osmium has still not appeared as a usable metal. It has merely moved from an almost invisible trace in rock to a less invisible trace in a chemically complicated residue. The next difficulty comes from family resemblance. Platinum, palladium, rhodium, ruthenium, iridium, and osmium share many chemical qualities. They resist attack by ordinary substances and can form related compounds. A process that dissolves one may also affect another. A reaction that leaves one behind may trap small amounts of its neighbours. Separation therefore requires a planned sequence rather than a single filter. Refiners use differences in solubility, electrical behaviour, oxidation state, and volatility. Platinum and palladium can be moved into solutions and recovered through selective reactions. Rhodium and iridium require other treatments. Ruthenium and osmium are unusual because they can form volatile tetroxides under strongly oxidizing conditions. This gives the refinery a way to separate them from metals whose compounds remain in the vessel. Volatility is helpful only when the equipment is designed to control it. Osmium tetroxide is highly toxic and can seriously damage the eyes and lungs. Industrial systems therefore use sealed vessels, extraction, scrubbers, monitoring, and carefully trained staff. The vapour is not allowed to wander around the building while everyone opens doors and hopes for the best. Official workplace guidance treats exposure at extremely low concentrations as a serious hazard. In simplified terms, osmium in the residue is converted under controlled conditions into the volatile tetroxide. The vapour is carried into a separate receiving system, where it is captured in a suitable solution. Other metals remain behind or are collected elsewhere. The refinery can repeat purification steps because ruthenium may behave similarly, and small amounts of other substances can travel with the osmium. This is not a method for a home laboratory. It involves powerful oxidizing conditions, corrosive chemicals, toxic vapour, and valuable material that is easy to lose. A person attempting it with improvised glassware would be combining financial disappointment with a medical emergency, which is an inefficient way to spend an afternoon. Once captured, the osmium compound must be purified. Chemists may change its chemical form, precipitate it from solution, redissolve it, and repeat the process until unwanted metals fall below the required limits. Each transformation is selected because osmium behaves slightly differently from its neighbours under those exact conditions. The sequence resembles sorting 6 sets of nearly identical buttons by placing them in different liquids, and observing which ones object first. Analysis follows every important stage. A refinery cannot judge purity by colour alone. Samples are tested using techniques that can distinguish tiny concentrations of neighbouring elements. Modern methods may examine how atoms absorb or emit light, or separate ions by mass. The results tell operators whether a stream should move forward, return for additional purification, or be combined with another batch. Recovery is important because the quantities are small. A residue that appears to contain almost no osmium may still be worth processing, when many tons of feed have passed through the plant. Dust, filters, furnace linings, wash solutions and old equipment can hold accumulated platinum group metals. Refineries often treat secondary residues and recycle internal materials rather than allowing rare atoms to leave in waste. This creates an unusual kind of housekeeping. In an ordinary kitchen, wiping a surface removes crumbs. In a precious metal refinery, cleaning a vessel may recover material valuable enough to be measured and returned to the process. The cloth, filter, or protective clothing may itself need controlled treatment. Nobody casually shakes the dust into a bin and assumes it has lost interest. After sufficient purification, the osmium compound is reduced to metallic osmium. The immediate product is often a fine black or grey powder, rather than a shining solid bead. Producing powder is easier than melting a large quantity, because osmium has an extremely high melting point. The powder can reach very high purity, but its fine form requires care. It presents a large surface area to air and can slowly form osmium tetroxide. Turning the powder into a dense solid creates another manufacturing problem. Powder metallurgy offers one route. The particles are pressed together and heated in a controlled atmosphere so that atoms move across the contact points and bind the mass. This process is called sintering. It takes place below the temperature required to melt the entire object. Though osmium still demands high temperatures and careful control, sintering osmium is not easy. The atoms do not move through the solid as readily as they do in many other metal powders, so pores can remain between particles. Recent research on the densification of nano-sized osmium has examined how heating rate, pressure, particle size, and atomic diffusion influence the final density. The work reflects a basic difficulty that runs through the whole story. Even after osmium has been found, concentrated, separated, purified, and reduced to metal, persuading it to become a fully dense object remains a specialized task. Some applications do not require a large solid piece. Powder can be used to prepare targets for depositing thin films, or it can be combined with other metals to form hard alloys. Small crystals may be grown or treated for collectors and decorative uses. A refinery chooses the final form according to the customer, because a laboratory reagent, an alloy ingredient, a coating target, and a display sample have different requirements. Purity is also defined by purpose. A research laboratory may need exact information about trace contaminants. An industrial alloy may tolerate more of a neighbouring platinum group metal. A collector may care about appearance and certification. The phrase pure osmium sounds absolute, but commercial materials always carry a measured specification and a limit below which impurities are accepted. The finished mass can be astonishingly small compared with the material that entered the mine. Many tons of ore may contribute to a quantity that fits inside a small bottle. The refinery has performed a long act of subtraction. Rock was removed, then silicate, then iron, sulfur, nickel, copper, and other precious metals. What remains is not a substance created by the process. It is a substance that was present from the beginning, hidden so thoroughly that almost everything around it had to be taken away. This is why the price of a rare refined metal cannot be understood from scarcity alone. It reflects exploration, mining, electricity, furnaces, water, chemical plants, analytical laboratories, safety systems, skilled labour, waste management, losses, and the fact that osmium supply depends on industries mainly interested in other metals. The tiny final sample carries a portion of every one of those costs. recycling can shorten the journey. Old catalysts, specialized alloys, electrical contacts and laboratory materials may contain platinum group metals. Secondary refiners collect these objects, sample them, concentrate the valuable portion, and apply chemical separation methods. Recycling avoids mining new rock for every recovered atom, but the feed can be more varied and difficult to analyse. A box of industrial scrap is less geologically complicated than a mountain, and more administratively complicated than anyone expects. Osmium recycling is limited by its small and specialised uses. There are not millions of osmium objects returning from households each week. Much of the metal exists in laboratories, industrial inventories, alloys, and products containing very small amounts. Recovering it makes sense when the material is collected in a controlled stream. Searching ordinary rubbish for osmium would mostly produce experience with rubbish. At the end of the process, the densest natural element can finally be weighed, sealed, labelled, and sent to a customer. It may travel as powder, sponge, crystal, compound, alloy, or a small consolidated piece. The package can look almost comically modest compared with the mine and refinery behind it. The purpose of all this effort is not simply to prove that the metal can be obtained. Osmium has been recovered because small amounts can perform jobs that softer or less durable materials cannot, because its compounds can reveal structures inside cells, and because its unusual physical behaviour is useful in highly specialised technologies. Once the metal leaves the refinery, its next destination may be the tip of a pen, the contact point of an instrument, a laboratory microscope, or a component designed for conditions far removed from the rock in which it was found. A refined piece of osmium may have travelled through a mine, a flotation plant, a furnace, several chemical vessels, and a tightly controlled purification system, only to end up on the tip of a pen. That can sound like a disappointing conclusion for an element formed in ancient stars, but the tip of a pen is exactly the sort of place where osmium makes sense. The component is tiny, the surface experiences repeated friction, and wear must be kept to a minimum. Osmium is rarely useful when a large object is required. It becomes much more attractive when a very small object must remain hard for a very long time. Early fountain pens presented a practical problem. The tip of the nib moved across paper whenever a person wrote, and paper is more abrasive than it feels. A soft metal tip gradually wears down. The shape changes, the line becomes less consistent, and the pen may begin to scratch or drag. Gold was an excellent material for the body of a nib because it resisted corrosion and could flex slightly, but pure gold was too soft for the point that touched the page. Manufacturers solved this by attaching a tiny bead of harder material to the end. Osmium-containing alloys were among the materials used for these points. The amount was extremely small, but that was enough. The writer received a durable surface without having to hold a pen made entirely from one of the densest substances on Earth. A solid osmium fountain pen would have made signing a letter feel like a minor strength test. These tips were sometimes called iridium points, even when the actual material contained a mixture of platinum group metals rather than pure iridium. Osmium and iridium occur together naturally and form very hard alloys. The exact composition changed with the available material and manufacturing process, but the purpose remained the same. The hard grain at the end of the nib accepted the wear, while the rest of the pen provided flexibility, shape, and comfort. The Royal Society of Chemistry lists fountain pen tips among the established uses of hard osmium alloys, and notes that the metal was employed for pen nibs because it was extremely resistant to wear. A pen point reveals an important principle of engineering. An entire object does not need to be made from the most durable material. Only the area facing the greatest stress may require it. A shoe has a tougher sole than upper. A drill has a hard cutting edge attached to a body designed to absorb force. A pen can have a flexible gold nib with a microscopic hard tip. This approach reduces cost, weight, and manufacturing difficulty while placing the unusual material exactly where it earns its keep. Gramophone needles offered a similar job. Early sound recording systems reproduced music through physical contact. A needle travelled along a groove in a rotating record, responding to tiny variations in its shape. The movement was converted into sound by mechanical or electrical equipment. The contact point had to follow the groove accurately, but every journey around the record caused wear. A needle that wore unevenly could reduce sound quality and damage the groove. Hard alloys containing osmium were used because they maintained their shape better than softer metals. Again, only a minute amount was needed. Osmium did not provide the music, store the recording, or turn the disc. It simply survived at the point where one surface repeatedly met another. Osmium alloys were also historically used in phonograph needles and other small wear-resistant components. The same logic led to instrument pivots and bearings. A pivot is a small point or shaft around which part of a mechanism turns. In a precision instrument, even slight wear can alter the movement. A compass needle, measuring device, or delicate mechanical mechanism may depend on a contact surface remaining smooth and correctly shaped. A hard osmium alloy could reduce wear while occupying very little room. This was especially useful before modern ceramics, synthetic gemstones, and advanced steels became widely available. Engineers had fewer choices for surfaces that needed to remain accurate through repeated movement. Platinum group alloys were expensive, but a tiny pivot required very little material. The cost could be justified in a scientific instrument, a watch, or a navigation device, where reliability mattered more than producing millions of cheap parts. Osmium alloys also appeared in needles used for specialized purposes. A needle concentrates force into a very small area, so its tip must resist deformation. If it becomes blunt, it no longer performs the same task. Hardness is valuable here, but brittleness must still be managed. A long needle made from pure osmium would be likely to fracture. A small hard portion, or an alloy, can provide wear resistance, without asking pure osmium to behave like flexible steel. Electrical contacts create another demanding surface. When two parts of a switch meet, electric current must pass through the contact point. The surfaces may touch and separate thousands or millions of times. Each movement can cause mechanical wear. Electrical sparks may create local heating, and contamination or corrosion can increase resistance. A hard, corrosion-resistant alloy can remain reliable under these conditions. Osmium has been used in specialized electrical contacts because it tolerates wear and does not react easily in its compact metallic form. It has never replaced copper as an ordinary conductor. Copper is cheaper, lighter, easier to shape, and highly conductive. Osmium is considered only when the contact area is very small, and durability is more important than cost or convenience. This distinction prevents a common misunderstanding. A material can be useful in an electrical device without being used for the wires. Copper is excellent for carrying current over a distance. Osmium alloys can be useful where two components physically meet. The bulk conductor and the contact surface have different jobs, so they benefit from different properties. Many of these mechanical applications are now less important than they once were. Better steels, tungsten-based materials, ceramics, synthetic sapphire, and other engineered substances can provide excellent wear resistance at lower cost or with easier manufacturing. Modern fountain pen tipping materials often rely on mixtures of very hard platinum group metals, and the word iridium may survive as a traditional description even when the composition is different. Osmium has not disappeared from technical use, but it has never had the large industrial market enjoyed by platinum, palladium, or rhodium. Its rarity, brittleness, high melting temperature, and difficult chemistry limit demand. The Royal Society of Chemistry describes it as having only a few uses, mainly in hard alloys and as a catalyst. That modest list is more accurate than claims suggesting that osmium is hidden inside every advanced machine. The catalytic role moves osmium away from surfaces that resist wear and into reactions involving molecules. A catalyst helps a chemical reaction proceed through a more accessible route. It participates in intermediate steps but is regenerated by the end of the process, at least in the ideal description. This means a relatively small amount can help transform a much larger amount of starting material. Osmium is particularly well known in organic chemistry through reactions involving osmium tetroxide. One important use is converting a carbon to carbon double bond into a product containing two neighbouring alcohol groups. Those products are known as diols and appear as useful building blocks in the preparation of medicines, natural products, and other complex chemicals. The reaction is valuable because the two new groups can be added to the same side of the original molecular structure. Chemists care greatly about such three-dimensional details. Two molecules can contain the same atoms connected in the same order and still behave differently because their structures are arranged as mirror images. A biological system may accept one arrangement and respond poorly to the other, rather like a left glove refusing to become useful on a right hand through positive thinking. Osmium-based methods can control this arrangement with high precision when the metal is combined with carefully chosen organic molecules called ligands. The ligands influence which side of the starting material approaches the reactive osmium center. This allows chemists to favor one three-dimensional product over its mirror image. The development of catalytic asymmetric oxidation methods, including asymmetric dihydroxylation, became an important part of modern synthetic chemistry. Barry Sharpless received part of the Nobel Prize in Chemistry in 2001 for work on chirally catalyzed oxidation reactions. The Nobel presentation specifically recognized the importance of his epoxidation and dihydroxylation methods for building complex molecules. Osmium tetroxide is expensive, volatile, and highly toxic, so a practical reaction should use as little of it as possible. Chemists often use a small catalytic quantity, together with another substance that returns the osmium to its active state after each reaction cycle. This allows the same osmium atoms to assist repeatedly, instead of requiring a full equivalent for every molecule of product. Researchers have also developed methods that attach osmium compounds to solid supports, or keep them within phases that can be separated from the product. The goal is to recover and reuse the catalyst while reducing the chance of osmium contamination. These systems do not make the compound harmless, but they can improve control and reduce waste when correctly designed. Research on reusable osmium catalysts has shown that supported systems can retain activity in asymmetric dihydroxylation reactions. A catalyst is sometimes described as though it performs effortless magic, but industrial and laboratory chemistry is less accommodating. Catalysts can become contaminated or lose activity. Small amounts may escape into product streams. Recovery may be incomplete. Every step must be analysed, especially when the catalyst contains a rare and toxic element. Osmium is useful because it can perform selective chemistry that is difficult to achieve by simpler routes. It is not chosen because chemists enjoy increasing the number of safety forms. Its most familiar scientific use is not found in a chemical factory but beside an electron microscope. Ordinary light microscopes are limited by the wavelength of visible light. Electron microscopes use beams of electrons and can reveal much smaller structures, including membranes and fine details inside cells. Biological samples, however, are made mostly from light elements that do not scatter electrons strongly. Without preparation, many structures produce weak contrast and can be difficult to distinguish. Osmium helps because its atoms are heavy. When an osmium compound becomes associated with part of a biological sample, that region scatters electrons more effectively and appears darker in the final image. The same high atomic mass that makes the metal dense also allows it to serve as a marker inside material that would otherwise look faint. Osmium tetroxide reacts strongly with unsaturated lipids, which are important components of cell membranes. During sample preparation, it helps preserve these membranes and adds electron-dense material to them. The outer boundary of a cell, the membranes surrounding internal compartments, and other lipid-rich structures become easier to see. Researchers can then examine the organisation of cells at scales far below the reach of an ordinary classroom microscope. The process does not involve pouring osmium over a living subject and placing it beneath a microscope. Small samples of tissue or cells are fixed, treated, dehydrated, embedded in resin, and cut into extremely thin sections. Each stage is designed to preserve structure while preparing the material for the electron beam. Osmium treatment is one part of a longer procedure. This preparation helped researchers study mitochondria, nerve cells, bacteria, muscle fibers, cell junctions, and the intricate membranes found throughout living tissue. In neuroscience, large samples can be stained with heavy metals so that extremely detailed networks of cellular structures can be reconstructed. Osmium remains widely used because it provides strong contrast in membranes, even though the staining process must be controlled carefully and can take considerable time. Recent research continues to investigate exactly which osmium-containing species form inside stained membranes and how they generate the electron microscope signal. The safety requirements are strict. Osmium tetroxide can injure the eyes, skin, and respiratory system at very low concentrations. It is handled in suitable ventilation, with protective equipment, sealed containers, and procedures for dealing with spills and waste. The unpleasant smell is not a useful warning system because dangerous exposure can occur at concentrations that should never be approached deliberately. Official occupational guidance identifies laboratory workers using it for transmission electron microscopy as one of the groups requiring protection. Osmium compounds have also been used to stain certain plastics and polymers. A manufactured material may contain regions with different chemical compositions that are difficult to distinguish under an electron microscope. Selective staining can make one region darker than another, revealing the microscopic structure. This helps researchers understand why a polymer bends, breaks, stretches, or responds to heat in a particular way. Fingerprint detection is another specialised application that has been reported for osmium tetroxide. Fingerprints contain oily substances left by the skin. Because the compound reacts with unsaturated materials, it can darken parts of a print and improve visibility on certain surfaces. The toxicity and difficulty of handling it make this far less convenient than routine fingerprint methods, so it remains a specialised technique rather than something carried in every police officer's pocket. PubChem lists both biological staining and fingerprint detection among recorded applications. Research involving metallic osmium and osmium nanoparticles has expanded the list of possible uses without turning most of them into large commercial industries. Very small metal particles provide a large surface area compared with their mass. This can make them interesting catalysts for reactions involving fuels, pollutants, or industrial chemicals. Researchers have examined osmium nanoparticles in electrochemical reactions, sensors, fuel cell-related systems, and methods for enhancing signals produced by light interacting with molecules. These studies demonstrate what osmium can do under controlled experimental conditions. They do not mean that osmium nanoparticles are already common in cars, phones, or power stations. A laboratory result must pass several tests before becoming a product. The method must be reliable, scalable, safe, affordable, and better than available alternatives. Osmium often performs well in the first test, and then meets the familiar problems of rarity, toxicity in oxidized forms, and cost. The same caution applies to medical research. Osmium compounds have been investigated as possible tools in diagnosis and treatment, because metal complexes can interact with biological molecules in unusual ways. Researchers can alter the molecules surrounding an osmium atom to change where a compound travels and how it reacts. This is an active area of chemical investigation, but experimental potential should not be confused with an established medicine. The difference between a promising result in cultured cells and an approved treatment is large, expensive, and filled with clinical trials. The densest element also appears in geochemical laboratories, though here it is often measured rather than used as a mechanical material. The proportions of different osmium isotopes can reveal the origins and ages of rocks, meteorites, and ore deposits. researchers dissolve carefully selected samples, separate the osmium, and measure its isotopic composition with sensitive instruments. A quantity too small to see clearly may provide evidence about events that occurred billions of years ago. The relationship between rhenium and osmium gives geologists a way to study time because one isotope of rhenium slowly changes into an isotope of osmium. Osmium isotope measurements can also help distinguish material from Earth's mantle, crust, and meteorites. In this role, the element is not valued for hardness or density. It is valuable because its isotopes preserve a measurable record of geological processes. High-pressure researchers use osmium as a subject rather than a tool. They place tiny samples between diamonds and compress them, while measuring changes in crystal structure and electronic behavior. The aim is to learn how one of the least compressible metals responds under pressures comparable with those deep inside planets. The osmium may not perform a task in the finished device. Its behavior is the information being collected. Space provides one of the best examples of the difference between an interesting property and a successful application. Osmium has been considered as a reflective coating for instruments working with far ultraviolet light. A very thin metal coating can reflect wavelengths that ordinary mirrors handle poorly. Because the layer is extremely thin, the high density adds little total mass. Samples of osmium optical coatings were flown aboard the Space Shuttle during Flight STS-8 as part of an experiment studying how materials responded to the low Earth orbit environment. The researchers were interested because earlier osmium coatings exposed in space had appeared to vanish. The shuttle experiment supported the explanation that atomic oxygen reacted with the osmium and formed a volatile oxide, allowing the coating to erode away. Platinum and iridium samples survived much better. Atomic oxygen is produced in the upper atmosphere when ultraviolet radiation separates ordinary oxygen molecules. Individual oxygen atoms are highly reactive. A spacecraft in low Earth orbit travels through this thin environment at high speed, so exposed surfaces experience repeated impacts. Materials that remain stable in a room can erode, darken, crack, or lose their optical properties in orbit. For osmium, the problem is especially unfortunate. The surface reacts to form the same volatile oxide that creates difficulty in laboratories. Instead of remaining as a durable mirror, the coating can leave the spacecraft molecule by molecule. A NASA spacecraft materials guide advises against using osmium in low Earth orbit because it reacts strongly with atomic oxygen and erodes. This means the phrase from fountain pens to spacecraft needs a careful explanation. Osmium has reached spacecraft as an experimental optical material, but the experiment helps show where it should not be used. That is still a useful result. Engineering advances not only by discovering materials that succeed, but also by identifying failure before an important mission depends on them. A failed coating in a controlled shuttle experiment is much better than a failed telescope mirror after launch. Once a spacecraft is in orbit, replacing a surface may be impossible. Materials are therefore tested under vacuum, radiation, temperature cycling, vibration, and exposure to reactive particles. A substance with impressive properties on Earth can behave differently when those conditions are combined. Osmium is also poorly suited to the main structure of a spacecraft. Launch vehicles must accelerate every kilogram against Earth's gravity. Designers reduce mass wherever possible because extra mass requires more fuel, larger equipment, or reduced payload. Aluminium alloys, titanium, carbon composites, and other materials provide high strength while remaining relatively light. Osmium provides the opposite benefit. It places exceptional mass into a small volume. There may be rare situations where a compact counterweight, contact, or tiny wear-resistant part could benefit from a dense platinum group alloy. Even there, tungsten, iridium, or other materials are usually easier to justify. Osmium is not a standard metal for spacecraft frames, fuel tanks, heat shields, or engines. Its journey into orbit has been more important as a lesson in surface chemistry than as the beginning of an osmium spacecraft industry. Beyond low Earth orbit, atomic oxygen becomes less relevant. but the other limitations remain. Osmium is rare, brittle, hard to manufacture and expensive. A coating protected from oxygen might retain useful optical behaviour, yet it would still compete with established materials that have longer engineering histories. Space agencies prefer substances with reliable test data, controlled supply chains, and predictable manufacturing. An unusual element must offer a clear advantage before anyone places it on a mission costing hundreds of millions. That is the pattern behind nearly every real use of osmium. It succeeds when only a tiny amount is needed, and one special property matters greatly. On a fountain pen, hardness matters. In a Yee pivot, where resistance matters. In a chemical reaction, catalytic selectivity matters. In an electron microscope sample, high atomic mass and lipid reactivity matter. In a geological analysis, isotope composition matters. In a spacecraft experiment, its failure under atomic oxygen matters. No single application uses every remarkable property at once. The density that made osmium famous may be irrelevant to a chemical catalyst. The volatile oxide that creates a safety problem becomes useful for staining membranes. The hardness that protects a pen point contributes little to isotope analysis. A material is not one fixed set of advantages. Its value changes with the scale, form, environment, and problem. This is why osmium is more instructive than its short list of commercial uses suggests. It shows that extreme properties do not guarantee widespread demand. The heaviest natural element has spent much of its practical history in objects measured in millimeters, in chemical quantities measured carefully inside sealed vessels, and in films so thin that they disappeared after meeting the wrong kind of oxygen. The next question is therefore larger than where osmium is used. Its limited uses tell us something about how science and engineering judge materials, why records can be less important than combinations of properties, and what an unusually dense metal reveals about the matter making up Earth and everything beyond it. The useful thing about an extreme material is that it forces us to define what we mean. Osmium is called the heaviest material on Earth because a small volume of it contains more mass than the same volume of any other naturally occurring element under ordinary conditions. That statement sounds simple, but it brings together several different ideas. It involves the structure of atoms, the arrangement of solids, the formation of planets, the behaviour of gravity, and the practical judgment required when choosing a material for a real job. The first lesson is that matter does not become impressive through one property alone. Osmium is dense because its atoms are heavy, and because those atoms occupy relatively little space in the metal. Gold has atoms that are slightly heavier on average, but gold atoms take up more room in the solid. Lead feels heavy in the hand, but its atoms are not packed closely enough to challenge osmium. Tungsten is hard, heat-resistant and dense, yet it still places less mass into the same volume. Osmium reaches its record through a particular combination rather than through one isolated feature. This is how materials usually work. A bridge cannot be designed by asking for the strongest substance and stopping there. The material must also be affordable, available, resistant to weather, easy enough to shape and able to survive repeated loads without cracking. A spacecraft material must be strong while remaining light. A medical implant must tolerate the body as well as mechanical stress. A kitchen spoon should not react with food, bend too easily, cost more than the kitchen, or require protective ventilation. Osmium performs brilliantly in a few categories and poorly in others. It is extremely dense, hard, resistant to wear, and difficult to compress. It also has a very high melting point. At the same time, it is brittle, rare, hard to manufacture, and capable of forming a dangerous volatile compound under certain conditions. These properties do not cancel one another. They exist together, and the engineer must consider all of them. That is why the densest element has not become the most useful metal. Iron and aluminium are found in ordinary structures because they can be produced in large quantities and shaped into useful forms. Copper fills electrical systems because it conducts well and can be drawn into wire. Titanium is used where strength and low mass matter. Osmium is reserved for cases where a tiny quantity can provide a specific advantage. A pen tip, a contact point, a catalyst, or a microscope stain asks much less of the supply than a railway bridge. The second lesson concerns the meaning of empty space. People often hear that atoms are mostly empty space and conclude that a solid object should be easy to compress. If most of an atom is not occupied by a hard particle, why can we not push the atoms together like soft bags in a suitcase? The answer is that atomic space is not empty in the ordinary sense. Electrons occupy regions around the nucleus, and their behaviour is governed by quantum rules. When the electron regions of neighbouring atoms are forced too close, the energy of the system rises sharply. Electrons cannot all settle into the same states, and electrical interactions resist further compression. The object feels solid because those interactions oppose the motion of your hand. Osmium demonstrates this resistance especially well. Its atoms already sit close together, and reducing the volume requires enormous pressure. There are no large air pockets between them that can simply close. The available arrangement is already efficient. Compressing the metal means forcing electron regions into conditions they strongly resist. This also explains why touching an object does not involve the nuclei in your hand, making direct contact with the nuclei in the object. The sensation of contact comes from electromagnetic and quantum interactions between the outer parts of atoms. When you press a finger against a table, the matter in the table pushes back through those interactions. The nuclei remain separated by distances that are tiny to us, but large compared with the nuclei themselves. Osmium therefore teaches us that solidity is not the same as a collection of miniature solid balls packed without gaps. A metal is a structured quantum system. Its atoms share and rearrange electrons through metallic bonding. The strength, hardness, conductivity, colour, and density of the material emerge from that arrangement. Change the element or the crystal structure, and the result changes even when the object still looks like an ordinary piece of metal. The word emerge can sound vague, but the process is practical. One isolated osmium atom does not have the hardness of a block of osmium. It does not have a polished surface or a melting point in the normal material sense. Those properties appear when a great number of atoms interact and form a solid. A single water molecule is not wet. Wetness describes how many water molecules behave together and how they interact with a surface. Material properties belong to organised collections. The third lesson is that weight and density are not the same. Osmium is dense, but a tiny piece can still be light. A grain of osmium does not outweigh a large steel beam. Total mass depends on both density and volume. The phrase heaviest material is convenient, but densest element is more precise. Weight also depends on gravity. Take an osmium sample to the moon, and its mass remains unchanged, but it weighs less because the moon pulls on it less strongly. Carry it to a planet with stronger surface gravity and it weighs more. The internal density of the sample may change slightly under different pressure and temperature conditions, but its identity does not depend on how difficult it is to lift. A kilogram of osmium and a kilogram of feathers have the same mass. On the same planet, they also have the same weight, provided air effects are ignored. The osmium occupies far less space. This familiar comparison is often treated as a joke, but it separates two ideas that are easy to confuse. A scale responds to total mass under gravity. Density tells us how concentrated that mass is. Concentrating mass does not create unusual gravity at the scale of a small metal sample. A block of osmium does not pull nearby objects toward itself in a noticeable way. Its gravity is determined mainly by its total mass, just like the gravity of any other object. The block feels surprising because the eye estimates its mass from its size and guesses too low. Earth supplies the pull. Osmium supplies the misleading appearance. Large astronomical objects reveal what happens when density and gravity begin to affect each other much more strongly. A planet gathers enough mass for gravity to compress its interior. The pressure increases with depth. Materials in the core are denser than the same materials would be at the surface. Earth contains iron, nickel, and smaller amounts of other elements. under conditions that cannot be reproduced easily outside specialized laboratories. Osmium is rare in the crust, partly because it prefers metallic material, and much of it followed iron toward the core while Earth was forming. The accessible surface is therefore not a complete sample of the planet. The rocks beneath our feet are rich in some elements, and poor in others because melting, separation, volcanic activity, erosion, and chemical reactions have sorted matter over billions of years. This sorting shows that the periodic table is not evenly distributed. Oxygen and silicon dominate much of the crust. Iron is abundant in the planet as a whole, but concentrated strongly in the core. Hydrogen is common in the universe, yet relatively scarce in Earth's solid bulk. Osmium is rare near the surface because it was never produced in great abundance, and because planetary formation placed much of it beyond reach. A small terrestrial sample can therefore provide information about events on very different scales. Its isotopes point toward nuclear reactions in older stars. Its chemical association with iron and other platinum group metals records the formation and differentiation of planets. Its crystal structure reveals how heavy atoms arrange themselves. Its response to pressure helps researchers test models of matter inside planetary interiors. This does not mean that osmium is a perfect model for every deep Earth material. The core is not made from osmium, and its temperatures and pressures create conditions very different from a laboratory sample at room temperature. Researchers use comparisons carefully. They may study osmium because it has a similar close-packed structure, strong bonding, or useful electronic behavior. The purpose is to test specific ideas, not to pretend that the center of Earth is a large ball of expensive blue-grey metal. Beyond planets, the word dense takes on meanings that make osmium appear almost light. A white dwarf forms when a star like the Sun reaches the end of its active life and leaves behind a hot compact core. A mass comparable with the Sun can be squeezed into an object roughly the size of Earth. Matter there is supported by the quantum behavior of electrons under extreme compression. A neutron star is denser still. It forms after the collapse and explosion of a massive star. More mass than the Sun can be compressed into a sphere roughly the width of a city. Under those conditions, atoms cannot retain their ordinary structure. Electrons and protons are driven into different forms of matter, and the familiar distinction between separate atomic nuclei becomes difficult to maintain through much of the interior. Comparing osmium with neutron star matter is not a fair contest. Osmium is a normal solid made from intact atoms. Neutron star matter exists because gravity has forced material into an extreme state that cannot remain stable on a laboratory table. Remove a small portion from the star and it would not sit quietly in a display case. The pressure supporting that state would be gone and the material would change violently. The comparison is useful because it places the record in context. Osmium is the densest naturally occurring element under familiar surface conditions. It is not the maximum density allowed by nature. Scientific records always belong to a category and a set of conditions. The fastest animal on land is not the fastest object. The hottest day in one country is not the highest temperature in the universe. Osmium wins a meaningful and carefully limited competition. That limitation makes the claim stronger rather than weaker. Science becomes reliable by stating conditions instead of hiding them. At room temperature and ordinary pressure, using naturally occurring elemental solids, osmium sits at the top of the density list. Iridium is extremely close. Change the conditions or include compressed stellar matter, and the list changes completely. Osmium also shows why measurement deserves respect. The difference between osmium and iridium is small enough that scientists have examined crystal dimensions, sample purity, temperature, and experimental uncertainty in detail. A popular fact may fit into one sentence, while the work supporting it requires careful instruments and repeated analysis. The density of a physical sample can be measured from its mass and volume, but both measurements have limitations. A tiny pore changes the apparent volume, an impurity changes the mass. Thermal expansion alters the crystal dimensions. A powder is not equivalent to a fully dense solid. Researchers can also calculate density using atomic mass and the dimensions of the repeating crystal structure. The best answer comes from combining accurate data and being honest about uncertainty. This is a general lesson from the periodic table. The numbers printed in reference books may look final, but they are products of measurement. Atomic weights reflect isotope mixtures. Melting points depend on purity and pressure. Hardness values depend on the test method. A number can be precise without being universal. The same caution applies to claims about rarity and value. Osmium is genuinely scarce, yet scarcity does not guarantee demand. It can be expensive to refine while remaining difficult to sell. A collector's crystal, an industrial powder, and a laboratory compound may have very different prices. A promotional claim may present one specialized price, as though every gram of osmium has an automatic buyer waiting. Nature does not assign prices. Markets do. The universe made osmium rare through nuclear history and planetary sorting. Human beings decide whether that rarity is useful, decorative, inconvenient, or profitable. The answer changes with technology. A metal once valued for pen tips may lose that market when better materials appear. A hazardous compound may gain scientific importance because it reveals membranes inside cells. A failed spacecraft coating may still provide valuable engineering knowledge. This leads to another lesson. Failure can be a use. Osmium coatings exposed to atomic oxygen in low Earth orbit did not simply disappoint researchers. Their erosion showed how the surface reacted and helped guide later material choices. A test that proves something unsuitable can protect a future mission from a much more expensive failure. The same principle applies throughout science. A brittle sample teaches how cracks move. A difficult catalyst reveals which reaction step controls a process. A material that corrodes in one environment helps identify the chemical cause. Understanding limits is not separate from understanding usefulness. It is often the most useful part. Osmium has limits in abundance, manufacturing, safety, and mechanical behavior. Those limits prevent it from becoming a universal supermetal. They also make it a compact example of how real materials must be judged. Extreme density cannot compensate for every other weakness. High hardness cannot guarantee toughness. A high melting point cannot guarantee easy high-temperature service. Corrosion resistance in one form does not guarantee safety in every compound. Human technology advances by combining materials rather than expecting one substance to do everything. A modern device may contain steel for structure, copper for wiring, ceramics for insulation, polymers for flexibility, and thin coatings for protection. Each material is placed where its properties are useful. Osmium's history follows this pattern on a very small scale. It appears at a point surface catalyst site or stained membrane, while other materials perform the surrounding work. The densest element also changes how we think about size. A small object can carry more mass than expected, because the atoms within it are heavy and closely arranged. At the same time, those atoms were made through events far larger than Earth. The scale runs from a nucleus smaller than any microscope can show directly, to stars and mergers spread across the galaxy, to a metal sample small enough to rest on a fingertip. There is no need to turn that fact into mystery. The connection follows a clear chain. Nuclear reactions made heavy isotopes. Those isotopes entered interstellar gas and dust. The solar system formed from that material. Earth separated into layers. Geological processes concentrated traces of platinum group metals. Mining and refining isolated osmium. Atomic structure then determined how the final solid behaved in a hand. Every step can be studied. Telescopes observe stellar events. Detectors record gravitational waves. Meteorites preserve early solar system material. Seismic data reveal Earth's interior. Microscopes examine minerals. Chemical plants separate elements. X-ray measurements determine crystal structures. A single metal links these fields because the same atoms pass through all of them. The story also corrects a common impression that the elements are permanent items placed into the universe from the beginning. They have histories. Hydrogen and helium formed early. Stars built many lighter elements. Neutron capture events produced much of the heavy end of the periodic table. Radioactive decay continued changing some isotopes after planets formed. Matter is stable enough for a metal sample to last, but the population of elements has been shaped by change. Osmium itself may seem fixed once refined, yet its surroundings and uses continue to change. A sample can be alloyed, oxidized, dissolved, deposited as a film, measured for isotope ratios, or locked inside a collector's case. Its 76 protons define it as osmium through every chemical transformation. Change the electrons or the bonds and the substance behaves differently. Change the nucleus, and it becomes another element. That distinction between chemical and nuclear change is one of the most important ideas hidden inside an ordinary material. Chemistry rearranges electrons and connections between atoms. Nuclear processes alter the nucleus. The dangerous oxide that carries osmium's name contains the same kind of osmium nucleus as the dense metal. But the different bonding gives the compound completely different behavior. The stellar events that first created osmium had to perform the much harder task of building the nucleus itself. By the time a person lifts a small osmium sample, most of this history is invisible. The hand notices only that the object is heavier than expected. That simple surprise is enough to begin the investigation. Why is it heavy? Why is it rare? Why is it brittle? Why can one of its compounds move through air? Why did most of it sink toward Earth's core? Why did stars need neutrons to make it? Following those questions turns one metal into a route through atomic physics, chemistry, geology, astronomy, engineering, and biology. Osmium is not important because the world depends on large quantities of it. It is important because it makes several basic ideas unusually clear. Matter has structure. Properties depend on arrangement. Records depend on conditions. Useful materials require trade-offs. Earth's surface does not contain every element in the proportions found inside the planet. Heavy nuclei carry evidence of older stars. Small laboratory measurements can test explanations about events that happened billions of years ago. We began with the image of a small metal cube resting beside a cup. It looked ordinary until someone tried to lift it. After following the element through its discovery, density, rarity, origin, refining, and uses, the cube has not become less ordinary in appearance. It still does not glow, move, or announce its history. The difference is that its weight now has an explanation. It feels heavy because heavy atoms occupy a compact crystal. Those atoms are scarce because the processes that make them require unusual cosmic conditions. They are scarce near the surface because planetary formation carried much of the metal inward. The sample is expensive and uncommon because extracting tiny traces from complex ores demands a long industrial process. Its uses remain limited because an extreme property does not remove brittleness, toxicity concerns, or cost. If you are listening at the end of the day, you do not need to remember every isotope, mining stage, or laboratory application. The simplest idea is enough. A material can look quiet while carrying information from very large events. Osmium's density can be felt in the hand, but the reasons for it reach into the structure of atoms and the history of stars. Where are you listening from tonight, and what time has it become while we have been following this small piece of metal? Perhaps the room is darker now. Perhaps the sounds around you have become quieter. The osmium cube can remain on the imagined table, where it is safest and much easier on the furniture. If this journey helped you relax or gave you something useful to think about, you can leave a like, subscribe, and share it with someone who enjoys science at a calmer pace. There are many more ordinary-looking materials with less ordinary explanations, and each one gives us another way to understand how the physical world is put together. For now, let the weight of the metal stay on the table rather than in your thoughts. The atoms will continue holding their places without assistance. The stars that made them have already completed the difficult part. All that remains is the quiet room, the steady passage of the evening, and enough time to rest.